Welcome to our exploration of one of the most fascinating concepts in modern science, antimatter energy. Today, we'll delve into what antimatter is and why it holds such potential for the future of energy generation. This intriguing topic may sound like science fiction, but it's rooted in real physics and groundbreaking research. Antimatter is the opposite of ordinary matter. While matter is made up of protons, neutrons, and electrons, antimatter consists of antiparticles, which have the same mass but opposite charge. For example, the antiparticle of the electron is the positron, which carries a positive charge instead of a negative one. Understanding this fundamental difference is crucial as we look at the potential applications of antimatter. The journey of antimatter began in the early 20th century when physicist Paul Dirac predicted its existence through his work in quantum mechanics. Shortly thereafter, the first positron was discovered in 1932. Since then, antimatter has become a subject of intense study in particle physics. Its elusive nature and unique properties make it a fascinating area of research for scientists around the globe. Why is antimatter energy important? As we face mounting challenges in meeting global energy demands and combating climate change, the quest for sustainable and efficient energy sources is more critical than ever. Antimatter has the potential to provide a nearly limitless source of energy if we can harness it effectively. A single gram of antimatter could release as much energy as several tons of conventional fuel, making it an incredibly powerful energy source. Despite its potential, the journey to harnessing antimatter energy is fraught with challenges. The current methods of producing antimatter are extremely costly and inefficient. Right now, it takes about $62.5 trillion to create just 1 gram of antimatter. This staggering expense highlights the hurdles we must overcome before we can consider using antimatter as a viable energy source. In addition to production costs, we face significant challenges related to storage and containment. Antimatter annihilates upon contact with regular matter, which means we cannot simply store it in a jar. Scientists are exploring various techniques to keep antimatter isolated, such as magnetic traps and advanced vacuum systems. These methods are still in experimental stages and require further innovation. Research in antimatter is ongoing, with major institutions like CERN and NASA leading the way. Scientists are conducting experiments to understand antimatter better and to explore its potential applications. From advanced propulsion systems for space travel to energy generation, the implications of antimatter research are vast and exciting. The prospect of harnessing antimatter energy also raises essential questions about safety and ethics. The energy produced from antimatter reactions could be incredibly destructive if misused. This brings us to the importance of developing stringent safety protocols and regulations to prevent potential hazards. While the idea of using antimatter for energy production may seem far-fetched, it is essential to consider its implications in the context of future energy solutions. By addressing the challenges of production, storage, and safety, we may unlock a powerful tool for sustainable energy. Join us as we continue this journey into the world of antimatter energy and explore its potential, the challenges we face, and what the future may hold. Antimatter is composed of antiparticles, which mirror the properties of their matter counterparts, but possess opposite charges. For instance, where a proton has a positive charge, its antiparticle, the antiproton, carries a negative charge. This fundamental characteristic leads to intriguing interactions when matter and antimatter come into contact. The basic building blocks of antimatter include antiparticles, such as positrons, antineutrons, and antiprotons. Each of these antiparticles is created through high-energy processes, such as cosmic ray collisions or particle accelerator experiments. These conditions are essential, as they provide the energy needed to generate antimatter. In terms of structure, antimatter forms just like matter, with antiparticles combining to create antimatter atoms. An antiproton can combine with a positron to form antihydrogen, the antimatter equivalent of hydrogen. This similarity makes antimatter fascinating, as it allows scientists to study its properties alongside conventional matter. Antimatter is not just a theoretical construct, it exists naturally in our universe. High-energy phenomena such as supernovae and gamma-ray bursts can create antiparticles. Scientists have detected positrons in cosmic rays, showcasing that antimatter is indeed present in the cosmos, even if only in small quantities. While antimatter production is possible in laboratories, the scale at which it can be generated is minuscule compared to the vast amounts needed for practical applications. Current production methods yield only a few atoms at a time. This limited output poses significant challenges when considering the potential use of antimatter for energy generation. The annihilation process is what truly highlights the power of antimatter. When a particle of matter meets its corresponding antiparticle, they destroy each other in an explosive release of energy. This reaction converts mass into energy, aligning with Einstein's famous equation E equals mc squared, illustrating how a small amount of antimatter can yield a tremendous energy output. Antimatter plays a crucial role in the universe's balance, influencing processes in particle physics and cosmology. Understanding its composition and behavior helps us unravel the mysteries of the universe, including the matter-antimatter asymmetry observed in our cosmos. This asymmetry raises questions about why our universe is predominantly matter, despite the existence of antimatter. Research into antimatter composition provides insights into the fundamental forces that govern particle interactions. The study of these antiparticles helps refine our understanding of quantum mechanics and the standard model of particle physics. With each discovery, we move closer to unlocking the secrets of antimatter. As scientists work to create more antimatter, they are also investigating how to manipulate it for potential applications. The composition of antimatter not only influences its creation, but also how it might be utilized in energy systems. Innovations in this field could open new avenues for harnessing antimatter energy effectively. The challenge lies not only in generating antimatter, but also in understanding how it interacts with matter on a deeper level. These interactions can lead to breakthroughs in multiple scientific disciplines, potentially paving the way for advanced technologies. The interplay between matter and antimatter could inspire entirely new methods of energy production. Understanding the composition of antimatter also involves a study of its stability. Antiparticles tend to be less stable than their matter counterparts, leading to rapid annihilation upon contact with ordinary matter. This instability must be addressed to create viable applications for antimatter in energy generation. As we advance in our research and understanding, the quest for harnessing antimatter energy continues to intrigue scientists and engineers alike. The composition of antimatter represents a frontier in science, challenging us to rethink our approach to energy and propulsion. The potential rewards are immense, waiting for the right technological breakthroughs to bring them to fruition. The fundamental difference between antimatter and regular matter lies in the properties of their constituent particles. While matter is made up of particles like protons, neutrons, and electrons, antimatter consists of their counterparts, antiprotons, antineutrons, and positrons. This inversion of charge and other characteristics leads to unique interactions that are crucial to understand. One of the most significant contrasts is in their charges. A proton, which carries a positive charge, has an equivalent in the antiproton, which is negatively charged. Similarly, electrons and positrons have opposing charges, leading to fascinating consequences during interactions between matter and antimatter. When matter and antimatter come into contact, they annihilate each other, releasing energy in the process. This annihilation generates gamma rays and other high-energy particles, illustrating the potent energy transformation that occurs. This process is not just a scientific curiosity, it has profound implications for potential energy applications. The stability of particles also differs markedly between matter and antimatter. Antimatter particles tend to be less stable and have shorter lifespans compared to their matter counterparts. This instability presents challenges for storage and practical use, as even the slightest contact with matter can lead to immediate annihilation. Another key distinction is the role antimatter plays in the universe. Antimatter is incredibly rare compared to matter, leading scientists to question why our universe is primarily composed of matter. This imbalance is one of the greatest mysteries in physics and has sparked numerous theories about the early universe and its evolution. The properties of antimatter have been tested through various experimental setups. High-energy collisions in particle accelerators have created antiparticles, allowing researchers to study their behavior. These experiments provide insights into how antimatter interacts with matter and contribute to our understanding of fundamental physics. Antimatter's interactions with electromagnetic fields also reveal important differences. While matter can be manipulated by magnetic and electric fields, antimatter behaves similarly but in the opposite manner due to its opposite charges. This characteristic can be exploited in experiments to control and study antimatter in laboratory settings. In terms of energy density, antimatter holds tremendous potential. The annihilation of even a small amount of antimatter can produce significant energy, making it a powerful candidate for future energy solutions. This high energy yield makes antimatter a subject of great interest for scientists exploring advanced propulsion systems and energy generation methods. Moreover, the creation of antimatter requires extreme conditions not typically found in our everyday world. High-energy particle collisions are necessary to produce antiparticles, making antimatter production a complex and resource-intensive process. This difficulty in creation underscores the uniqueness of antimatter within the broader landscape of physics. The distinct behavior of antimatter also raises questions about fundamental symmetries in physics. The differences between matter and antimatter challenge our understanding of conservation laws and the fundamental forces that govern particle interactions. This exploration opens new avenues for research, seeking to explain the underlying principles of the universe. Antimatter not only captivates the scientific community, but also poses intriguing possibilities for future technologies. As we investigate its properties, we may uncover new methods for harnessing this unique form of energy. The quest for understanding how antimatter differs from regular matter could lead to groundbreaking advancements in various fields. By examining these differences, scientists are laying the groundwork for potential applications that could change how we think about energy and propulsion. The contrast between antimatter and matter serves as a reminder of the complexities of our universe, pushing us to explore beyond conventional boundaries. As we continue our journey into the realm of antimatter, the implications for energy and technology remain both exciting and challenging. Annihilation is a fundamental process that occurs when matter and antimatter meet. In this encounter, the particles collide, resulting in their mutual destruction and a remarkable release of energy. This phenomenon exemplifies the principles of mass-energy equivalence, where the mass of the annihilated particles converts into energy. The energy released during annihilation is immense. For instance, when a particle of matter interacts with its antiparticle, such as an electron meeting a positron, they annihilate, producing gamma rays. These high-energy photons are a direct indication of the powerful transformation that takes place during this interaction. The mechanics of annihilation can be explained through quantum field theory, which describes the behavior of particles and their interactions. When two particles collide, they can exchange energy, leading to the creation of new particles or the annihilation of existing ones. This process showcases the intricate nature of particle physics and the fundamental forces at play. Annihilation reactions are not limited to just one type of particle interaction. Various combinations can result in different outcomes depending on the particles involved. For example, the annihilation of a proton and an antiproton leads to the production of several other particles, including pions and kaons, illustrating the complexity of these interactions. The concept of annihilation is critical for understanding the energy potential of antimatter. A tiny amount of antimatter can yield an extraordinary amount of energy through annihilation, making it a tantalizing prospect for future energy sources. This vast energy release is why scientists are keen to explore the practical applications of antimatter. Annihilation also plays a crucial role in astrophysics. In extreme environments, such as near black holes or during supernovae, matter and antimatter interactions can occur, contributing to the energy dynamics of these cosmic events. Understanding these processes helps scientists gain insight into the universe's most energetic phenomena. Researchers utilize annihilation to study the properties of antimatter in laboratory settings. By observing the gamma rays produced during these reactions, scientists can gather data about the behavior and characteristics of antimatter particles. This experimental approach not only enhances our understanding, but also informs future applications. Despite the fascinating nature of annihilation, safety concerns must be addressed. The energy released in these reactions is vast, which raises questions about the potential for controlled use in practical applications. Developing methods to harness this energy safely will be essential for any future antimatter technology. Annihilation is also tied to theoretical explorations in physics. The asymmetry between matter and antimatter in the universe poses intriguing questions about why we observe more matter than antimatter. Analyzing annihilation processes may provide clues to this mystery, guiding researchers toward answers that could reshape our understanding of the cosmos. The implications of annihilation extend beyond energy production. They influence the fundamental laws governing particle interactions and the evolution of the universe itself. As scientists continue to unravel these complexities, we gain a deeper appreciation for the role of annihilation in both theoretical and practical contexts. The dual nature of annihilation, its capacity for destruction and energy release, offers a fascinating lens through which to view antimatter. Each interaction serves as a reminder of the intricate balance between matter and antimatter, shaping the very fabric of reality. Exploring this concept further could lead to groundbreaking advancements in our understanding of fundamental physics. As we probe the depths of annihilation, we are not just investigating a process but also unlocking the potential for future innovations. The quest to harness the energy from these reactions could revolutionize energy generation and propulsion systems. The journey into the concept of annihilation continues to intrigue scientists and engineers alike. The energy release from matter-antimatter reactions is a staggering demonstration of the power encapsulated within the universe. When a particle and its antiparticle collide, they annihilate each other, converting their entire mass into energy. This process adheres to Einstein's equation, E equals mc squared, which illustrates how mass can be transformed into energy at a remarkable efficiency. To put the energy potential into perspective, consider that just 1 gram of antimatter could yield approximately 90 terajoules of energy. This amount is equivalent to the energy released by the detonation of around 20 kilotons of TNT. Such a powerful energy release highlights why antimatter is often referred to as the ultimate fuel source. The annihilation process generates high-energy photons, primarily in the form of gamma rays. These gamma rays carry away the energy produced during the reaction and can be detected and measured in experiments. This detection allows scientists to study the properties of antimatter and the dynamics of annihilation in more detail. The efficiency of energy release in these reactions far surpasses that of conventional fuels. For example, chemical reactions like burning fossil fuels release only a fraction of energy per unit mass compared to antimatter. This vast difference is what makes antimatter so enticing for future energy solutions, as it offers a far greater energy density. Moreover, the energy from matter-antimatter reactions is not just theoretically significant. It has practical implications for space exploration. If harnessed effectively, antimatter could provide a propulsion system for spacecraft, enabling faster travel to distant planets or even other star systems. This potential revolutionizes our approach to interstellar travel. However, the challenge remains in how to effectively capture and utilize this energy. Current technology does not yet allow for the safe and efficient harnessing of the energy produced during annihilation. Developing systems that can convert this energy into usable power will be a critical step in moving forward. The reaction products, aside from gamma rays, include various particles such as pions, which are created during annihilation events. The presence of these secondary particles can complicate the energy release process. Understanding the dynamics of these products is vital for optimizing energy extraction methods. Additionally, energy release is influenced by the specific particles involved in the annihilation. For instance, the annihilation of a proton and an antiproton produces different energy signatures compared to the annihilation of an electron and a positron. These variations must be thoroughly examined to maximize the energy yield from antimatter interactions. The immense energy potential of antimatter also raises questions about safety and containment. A large-scale, uncontrolled reaction could lead to catastrophic consequences, necessitating stringent safety measures. Ensuring that future antimatter applications are safe will be paramount as research advances. Investigations into matter-antimatter reactions contribute to our understanding of fundamental physics. The behavior of particles during annihilation sheds light on the nature of forces and interactions in the universe. This research is not only about energy, it's also about unraveling the mysteries of matter and antimatter. The implications of harnessing energy from these reactions could extend beyond traditional energy systems. Concepts such as antimatter-based batteries or compact reactors are beginning to emerge in theoretical discussions. As research progresses, the potential applications of this energy could transform how we approach energy generation and storage. Each step forward in understanding energy release in matter-antimatter reactions brings us closer to realizing the possibilities of antimatter as a practical energy source. The journey to harness this energy remains filled with challenges, yet the rewards could redefine our technological landscape. As we explore this frontier, the potential of antimatter continues to inspire curiosity and innovation. The potential energy yield from antimatter is staggering, positioning it as a possible game-changer in the energy landscape. 1 gram of antimatter can release energy equivalent to that produced by several tons of conventional fuel, demonstrating its unmatched energy density. This capability makes antimatter an attractive subject for researchers looking to revolutionize energy production. The immense energy output stems from the annihilation process, where matter and antimatter convert their mass into energy almost entirely. To visualize this, consider that the annihilation of just a few particles can produce a measurable amount of energy, highlighting the effectiveness of antimatter as a fuel source. This efficiency far exceeds that of any existing energy resource. In practical terms, harnessing antimatter for energy could drastically change how we power everything from spacecraft to cities. The theoretical applications extend to antimatter propulsion systems, which could propel spacecraft to incredible speeds, enabling missions to distant planets in a fraction of the time compared to conventional methods. This potential reshapes our aspirations for space exploration. Yet the challenges of capturing and utilizing this energy yield must not be overlooked. Current methods for producing antimatter are prohibitively expensive and inefficient, with production costs reaching trillions of dollars per gram. To make antimatter a viable energy source, we need significant advancements in production techniques to reduce costs. Moreover, the infrastructure required to store and harness antimatter safely is still in its infancy. Effective containment solutions are crucial for preventing premature annihilation and ensuring that the energy can be tapped when needed. Developing reliable storage systems that can handle the volatile nature of antimatter is essential for future applications. Beyond space travel, antimatter holds promise for other sectors, including energy generation on Earth. If we can develop methods to convert the energy released from antimatter reactions into usable power, we might drastically reduce our dependence on fossil fuels. The implications of such advancements could lead to a more sustainable energy future. Understanding the energy yield also involves studying the various reactions that occur during annihilation. Different particles interact in unique ways, affecting the energy output of each reaction. By analyzing these processes, researchers can optimize the conditions for maximum energy efficiency, paving the way for practical applications. In addition to energy generation, antimatter could play a role in medical technologies. For instance, positron emission tomography, or PET scans, already utilizes antimatter principles to provide crucial diagnostic imaging. Exploring new applications in medicine could further enhance the impact of antimatter on our lives. The potential yield from antimatter energy also poses significant ethical and safety questions. The capacity for catastrophic energy release necessitates rigorous safety protocols to prevent misuse or accidents. As we consider harnessing antimatter, addressing these concerns will be paramount to ensuring a responsible approach to its application. Innovative research in this field continues to unfold, with scientists seeking ways to make antimatter more accessible. Breakthroughs in particle physics and engineering could eventually bring antimatter closer to practical use, transforming our energy systems. Each discovery in this area contributes to a broader understanding of the potential within antimatter. Furthermore, the excitement surrounding antimatter is generating interest and investment from both public and private sectors. Increased funding can accelerate research and development, pushing the boundaries of what is possible. As the scientific community collaborates, the prospects for antimatter energy become increasingly promising. The journey to unlock the potential energy yield from antimatter is filled with challenges, but also immense possibilities. The pursuit of this knowledge not only pushes the boundaries of science, but also offers a glimpse into a future where energy sources are more abundant and cleaner, As we delve deeper into antimatter, we edge closer to realizing its extraordinary potential. CERN, the European Organization for Nuclear Research, is at the forefront of antimatter research, conducting groundbreaking experiments to explore its properties and potential. One of their most significant projects, the antiproton decelerator, is designed to produce and study antihydrogen, allowing scientists to examine how antimatter behaves under controlled conditions. This facility provides a unique environment for probing the fundamental aspects of antimatter. The goal of CERN's experiments is to understand the differences between matter and antimatter on a deeper level. Researchers are investigating whether antimatter behaves in the same way as matter under various physical laws. This comparison could yield insights into the fundamental symmetries of the universe and why there appears to be more matter than antimatter. CERN's researchers create antihydrogen by combining antiprotons and positrons. The precision required in these experiments is immense, as even slight deviations can lead to significant variations in outcomes. By creating antihydrogen atoms, scientists can conduct tests to measure their properties and see how they compare to their matter counterparts. One fascinating aspect of these experiments is the study of antimatter gravity. Researchers are investigating whether antimatter is affected by gravity in the same way as matter. This inquiry could reveal new insights into our understanding of gravity itself and potentially reshape existing theories in physics. CERN also engages in international collaborations to advance antimatter research. By sharing knowledge and resources, scientists can conduct more comprehensive experiments and make significant strides in understanding antimatter. These partnerships extend the reach of research and enhance the global effort to unravel the mysteries of antimatter. The techniques used at CERN for antimatter production and study involve advanced particle accelerator technology. These accelerators collide particles at high speeds, generating conditions where antimatter can be produced. The ability to control these high-energy environments is crucial for creating stable antimatter samples for experimentation. One of the most significant findings from CERN's antimatter experiments is the measurement of antihydrogen's spectral lines. By comparing these lines to those of hydrogen, researchers hope to determine if there are any differences that could hint at new physics beyond the standard model. Such discoveries could have profound implications for our understanding of the universe. The research at CERN also touches on fundamental questions about the origins of the universe. The apparent imbalance between matter and antimatter is a central mystery in cosmology, and findings from CERN could help explain this phenomenon. Understanding the early moments of the universe may shed light on why matter prevailed. Safety protocols are paramount during these experiments due to the high-energy processes involved. The handling of antimatter requires strict guidelines to prevent accidental annihilation and ensure the safety of researchers. CERN has implemented robust measures to mitigate risks associated with antimatter experiments. Public outreach is another important aspect of CERN's work, as they strive to share their findings with the world. Through educational programs, exhibitions, and digital content, CERN engages the public in discussions about antimatter and its implications. This transparency fosters a greater understanding of the science behind antimatter research. CERN's commitment to advancing antimatter research is evident through their ongoing experiments and collaborative efforts. As they continue to push the boundaries of knowledge, the scientific community remains excited about the potential discoveries that lie ahead. Each experiment conducted at CERN brings us closer to unlocking the secrets of antimatter and its role in the universe. The research being conducted at CERN exemplifies the intersection of cutting-edge technology and fundamental science. As they investigate the mysteries of antimatter, they contribute to a broader understanding of physics that may one day change how we perceive energy and the cosmos. The journey through antimatter research is just beginning, with endless possibilities waiting to be explored. NASA is actively exploring the potential of antimatter as a revolutionary propulsion system for future space missions. The idea is that antimatter could provide an incredibly efficient means of travel, enabling spacecraft to reach distant planets in a fraction of the time compared to conventional methods. This ambitious approach aims to address the limitations of current propulsion technologies. One of the key advantages of antimatter propulsion is its high energy density. As previously mentioned, the annihilation of just a small amount of antimatter can yield vast amounts of energy, making it an attractive option for long-duration space missions. By harnessing this energy, spacecraft could achieve greater speeds and reduce travel time to destinations within our solar system and beyond. NASA's research includes concepts such as the antimatter catalyst engine, which utilizes antimatter to initiate reactions in conventional fuels. This hybrid approach could enhance thrust and fuel efficiency while leveraging the benefits of antimatter without requiring extensive storage systems. The integration of antimatter in propulsion could redefine how we think about spacecraft design and mission planning. To study these concepts, NASA has conducted various theoretical analyses and computer simulations. These models help scientists understand the dynamics of antimatter reactions and their potential applications in propulsion systems. Through rigorous testing and validation, researchers aim to identify viable pathways for incorporating antimatter into future missions. Safety remains a primary concern in any research involving antimatter, especially in propulsion systems. Given the explosive potential of antimatter, developing safe containment and handling methods is crucial. NASA prioritizes safety protocols to ensure that any experimental propulsion systems can operate without jeopardizing crew members or the spacecraft. Collaborations with other research institutions and private companies are also essential for advancing antimatter propulsion studies. By pooling resources and expertise, NASA can accelerate the pace of research and development. This collaborative spirit fosters innovation and helps tackle the complex challenges associated with antimatter applications. Investigations into antimatter propulsion are not limited to theoretical models. Experiments are underway to assess the feasibility of these technologies. Tests may involve particle accelerators to generate and manipulate antimatter, allowing researchers to observe its effects on propulsion systems. This hands-on approach is vital for bridging the gap between theory and practical application. NASA's interest in antimatter extends beyond propulsion. It also encompasses energy generation for long-term space missions. Harnessing antimatter for onboard energy systems could provide astronauts with a reliable power source during extended missions. Such advancements would enhance mission sustainability and open new frontiers in space exploration. The potential for antimatter propulsion also raises exciting possibilities for interstellar travel. With antimatter-powered spacecraft, humanity could envision missions to exoplanets, exploring worlds beyond our solar system. This capability could ignite interest in astrobiology and the search for extraterrestrial life. As research progresses, the challenges associated with antimatter storage and production will need to be addressed. Current methods of producing antimatter are expensive and time-consuming, necessitating advancements to make it feasible for propulsion applications. Efforts are focused on improving antimatter production techniques to make it a practical option for space travel. The idea of using antimatter for propulsion captures the imagination and represents a significant leap in our technological capabilities. As NASA continues to investigate this area, the implications for future missions could be transformative. Each step forward in understanding antimatter propulsion brings us closer to realizing our dreams of exploring the cosmos. NASA's commitment to studying antimatter propulsion reflects a broader vision of future space exploration. As the agency pushes the boundaries of what is possible, the potential to unlock new energy sources and travel capabilities becomes increasingly tangible. The journey into the realm of antimatter propulsion is just beginning, with possibilities that stretch far beyond our current understanding of space travel. Many universities around the world are at the forefront of antimatter research, pushing the boundaries of our understanding in this complex field. These institutions are conducting innovative experiments and theoretical studies that contribute to the broader scientific knowledge of antimatter. Their efforts are crucial in exploring the potential applications of this enigmatic substance. One prominent example is a leading university that has established specialized research programs focused on antimatter production. Here, scientists are investigating new methods for generating antimatter in more efficient ways. This research aims to reduce costs and improve the practicality of using antimatter in various applications. Another notable institution is actively studying the properties of antimatter through advanced particle physics experiments. Researchers are working with particle accelerators to create antihydrogen and analyze its characteristics. By comparing antihydrogen to hydrogen, They seek to understand fundamental differences that could illuminate the underlying principles of the universe. Several universities are also exploring the implications of antimatter in cosmology. They are investigating how antimatter fits into our understanding of the universe's evolution and the apparent imbalance between matter and antimatter. These inquiries could yield groundbreaking insights into the very fabric of reality. In addition to fundamental research, universities are offering interdisciplinary programs that integrate antimatter studies with fields like engineering and medicine. By training a new generation of scientists and engineers, these programs aim to cultivate expertise that could drive future advancements. This educational approach ensures that the next wave of researchers is well equipped to tackle the challenges ahead. Collaborative efforts between universities and research institutions enhance the impact of antimatter studies. Joint projects allow for the pooling of resources and expertise, leading to more comprehensive investigations. These collaborations can accelerate the pace of discovery, resulting in significant advancements in antimatter research. Some universities are also focusing on the safety and ethical implications of antimatter research. Understanding the risks associated with antimatter production and potential applications is crucial for responsible scientific progress. By addressing these concerns, academic institutions help set the standards for safe practices in the field. Public outreach initiatives led by universities play a vital role in raising awareness about antimatter and its potential benefits. By engaging with the community, these institutions promote scientific literacy and interest in complex topics. This outreach fosters a better understanding of antimatter research and its implications for society. Moreover, student-led projects are becoming increasingly common in university settings. These initiatives provide hands-on experience for aspiring scientists and allow them to contribute to ongoing research. Encouraging student involvement helps cultivate a culture of innovation and exploration within academic institutions. As funding for scientific research becomes more competitive, universities are seeking grants and partnerships to support antimatter studies. Many institutions are actively pursuing collaborations with government agencies and private companies. These partnerships can provide the necessary resources and funding to push research efforts further. The impact of university research on antimatter extends beyond academia. Discoveries made in these institutions often influence public policy and funding priorities. As universities lead the charge in antimatter research, their findings can shape the future direction of science and technology. Through their commitment to advancing antimatter research, universities are helping to illuminate the mysteries of this captivating field. Their contributions not only deepen our understanding, but also pave the way for potential applications that could change the landscape of energy and space travel. The collaborative spirit within academia is essential for unlocking the full potential of antimatter. Collaboration between nations is essential in advancing antimatter research, as the challenges posed by this field often exceed the capabilities of any single country. By pooling resources and expertise, countries can tackle complex problems and accelerate the pace of discovery. International partnerships have become a cornerstone of progress in this scientific frontier. One significant example of this cooperation is the collaboration among European nations through CERN. This multinational organization brings together scientists from various countries to work on particle physics and antimatter experiments. The shared goal is to deepen our understanding of fundamental particles and their interactions, benefiting all member states. Similarly, joint research initiatives between the United States and European institutions are helping to advance antimatter studies. These partnerships focus on specific projects, such as investigating the properties of antihydrogen and its implications for physics. By sharing data and methodologies, researchers can conduct more comprehensive experiments and validate their findings. Countries in Asia are also increasingly participating in antimatter research collaborations. Nations like Japan and China have invested in particle physics facilities that contribute to global research efforts. These investments allow for a more diversified approach to antimatter studies, enriching the scientific community as a whole. International workshops and conferences serve as platforms for scientists to exchange ideas and findings related to antimatter. These events foster dialogue and collaboration among researchers from different backgrounds and expertise. Through these gatherings, new partnerships often form, leading to innovative approaches to common challenges. Funding for antimatter research can be difficult to secure, especially given its high costs. Collaborative efforts enable countries to share the financial burden associated with large-scale experiments and infrastructure. By jointly funding projects, nations can maximize their resources and enhance the overall impact of their research initiatives. The implications of antimatter research extend beyond scientific discovery. They can also influence global energy strategies. By working together, nations can explore sustainable energy solutions that leverage antimatter's potential. This collaborative spirit may pave the way for innovative technologies that address pressing energy challenges. As researchers explore the complexities of antimatter, ethical considerations also come into play. International collaboration allows for a broader discussion of the safety and ethical implications surrounding antimatter research. By establishing common guidelines and protocols, nations can ensure responsible practices in the field. Educational exchanges and training programs are also important components of international collaboration. These initiatives allow young scientists to gain valuable experience in different research environments. As they learn from one another, they build a global network of experts who will drive future advancements in antimatter research. Collaborative efforts in antimatter research often lead to significant breakthroughs that benefit the entire scientific community. Discoveries made through international partnerships can influence policy decisions and funding priorities on a global scale. By working together, nations can push the boundaries of knowledge and understanding in this intriguing field. As countries continue to collaborate on antimatter research, the potential for innovation expands. The combined expertise and resources from diverse regions foster an environment where creativity and discovery can thrive. This interconnectedness among nations is essential for unlocking the full potential of antimatter. The journey into the realm of antimatter is not just a national pursuit but a global endeavor. As nations unite in their efforts to explore this fascinating subject, the collective impact can reshape our understanding of physics and energy. The collaborative spirit inherent in this research can pave the way for a brighter scientific future. The cost of antimatter production is one of the most significant barriers to its practical applications. Currently, it is estimated that producing just 1 gram of antimatter could cost around $62.5 trillion. This staggering figure stems from the complex processes required to create and isolate antimatter particles. To produce antimatter, scientists use particle accelerators that collide high-energy particles. These collisions can generate antiparticles, but the efficiency of this process is extremely low. For every particle created, a substantial amount of energy is consumed, contributing to the high production costs. The methods for generating antimatter are still in experimental stages and require significant technological advancements. Current facilities can only produce tiny amounts of antimatter, often measured in nanograms. This limited output further exacerbates the cost issue, making it challenging to scale up production for practical use. Moreover, the infrastructure needed for antimatter production is both expensive and complex. Building and maintaining particle accelerators involves substantial investment and technical expertise. The financial and logistical requirements can deter potential research initiatives, slowing progress in the field. Efforts are underway to explore alternative production methods that could reduce costs. Some researchers are investigating whether utilizing different materials or optimizing existing techniques can yield better results. Innovations in this area could lead to more efficient processes and lower the financial barriers associated with antimatter production. The storage and handling of antimatter also contribute to its overall cost. Due to its volatile nature, antimatter must be contained in specialized facilities that can prevent contact with regular matter. This necessity for sophisticated containment solutions adds another layer of expense to the production process. Additionally, the energy input required to produce antimatter is immense. The energy consumed in creating antimatter often outweighs the energy that could potentially be harnessed from it. This inefficiency highlights the need for breakthroughs in both production and energy extraction methods to make antimatter a viable resource. Global competition in antimatter research also plays a role in production costs. As more countries invest in antimatter studies, there is an opportunity for shared knowledge and resources. Collaborative efforts could lead to innovations that decrease production costs and make antimatter more accessible. Despite the challenges associated with high costs, the potential benefits of antimatter energy continue to drive research efforts. Scientists remain optimistic that advancements in technology will eventually lead to more feasible production methods. This determination is crucial for exploring the possibilities of antimatter in energy generation and propulsion. Some private companies are also investigating cost-effective ways to produce antimatter. By leveraging advancements in technology and engineering, these firms hope to contribute to lowering production costs. Their involvement may accelerate the pace of research and development, ultimately benefiting the entire field. The high cost of antimatter production serves as a reminder of the complexities involved in unlocking its potential. As researchers work to address these financial challenges, the dream of utilizing antimatter for energy and exploration remains alive. Overcoming these obstacles will be essential for the future of antimatter applications. The ongoing exploration of cost reduction strategies highlights the importance of persistence in scientific research. Each breakthrough, no matter how small, brings us closer to making antimatter a practical and viable energy source. The journey toward affordable antimatter production is a challenging yet exciting endeavor. The efficiency of current technology in antimatter production is a significant hurdle in making it a practical energy source. Current methods rely on particle accelerators to create antiparticles, but the energy output is minimal compared to the energy input required. This inefficiency makes large-scale production of antimatter economically unfeasible at present. Particle accelerators generate antimatter through high-energy collisions, where particles smash into each other at speeds close to the speed of light. Although this technique can produce tiny amounts of antimatter, it requires vast amounts of energy to operate. The overall yield remains low, meaning that the amount of antimatter produced is often not worth the energy invested in its creation. Another limitation lies in the time it takes to produce antimatter. Current technologies require extensive periods to generate even small quantities, further complicating the feasibility of antimatter as a usable resource. The slow production rate poses challenges for any future applications, particularly in fields like space travel or energy generation. Current storage methods also impact the efficiency of antimatter technology. Since antimatter annihilates upon contact with regular matter, it must be stored in specialized containment systems. These containment methods are not only costly but also complex, which adds to the overall inefficiency of working with antimatter. Researchers are actively seeking ways to improve the efficiency of antimatter production techniques. Innovations in accelerator technology, such as more powerful machines or novel approaches to collision processes, could enhance yield rates. By optimizing these systems, scientists hope to achieve a more favorable energy balance in antimatter production. Additionally, scientists are exploring alternative production methods that could bypass some of the limitations associated with particle accelerators. Approaches such as laser-based systems or utilizing natural cosmic ray interactions are being investigated. These methods may offer more efficient pathways for generating antimatter without the same energy demands as traditional techniques. The theoretical efficiency of antimatter as an energy source remains high, which motivates ongoing research despite current technological limitations. If harnessed effectively, antimatter could provide an energy output far exceeding that of conventional fuels. Bridging the gap between theoretical potential and practical application is crucial for the future of antimatter research. International collaborations are also playing a role in enhancing technology efficiency. By sharing knowledge and resources, scientists can identify best practices and innovative solutions to common challenges. This cooperative approach can accelerate advancements, leading to improved production methods and techniques. Moreover, the development of more advanced computational models is aiding researchers in optimizing antimatter production. Simulations can help predict outcomes under various conditions, guiding experimental efforts toward more efficient techniques. These models serve as valuable tools for understanding the complexities of antimatter interactions. Education and training in cutting-edge technologies are essential for advancing the field of antimatter research. As new generations of scientists are educated in these areas, they bring fresh ideas and perspectives to long-standing challenges. Empowering young researchers is vital for fostering innovation and efficiency in antimatter studies. The challenges associated with current technology efficiency underscore the need for continuous improvement and investment in research. Each step toward optimizing production processes can contribute to making antimatter a more viable resource. As efforts in this area progress, the dream of harnessing antimatter for practical applications becomes increasingly tangible. With the relentless pursuit of efficiency in antimatter production, scientists remain hopeful about the future. Each breakthrough, whether in technology or methodology, can reshape our understanding of antimatter and its potential. The quest for improved efficiency is not just a technical challenge, it's a crucial pathway to unlocking the possibilities of antimatter. The lack of infrastructure for large-scale antimatter production presents a significant challenge to its practical applications. Current facilities are primarily designed for research purposes, focusing on fundamental physics rather than mass production. This limitation restricts the ability to generate antimatter in quantities that could be useful for energy generation or propulsion systems. Building new facilities specifically tailored for antimatter production would require substantial investment. These installations would need to include advanced particle accelerators and specialized containment systems. The financial and logistical demands of such infrastructure can deter both public and private funding. Additionally, existing research facilities often face constraints in terms of operational capacity. Many particle accelerators are heavily utilized for various experiments, leaving little room for dedicated antimatter production efforts. This competition for resources can hinder the development of a robust infrastructure needed for large-scale production. Safety concerns further complicate the establishment of antimatter production facilities. Given the volatile nature of antimatter, any large-scale operation would need to prioritize stringent safety protocols. Implementing these measures requires additional resources and planning, which can slow the progress of infrastructure development. The technical complexity of antimatter production also necessitates specialized expertise. Skilled scientists and engineers are essential for designing and operating advanced production facilities. The current shortage of trained personnel in this niche field can impede efforts to build the infrastructure needed for large-scale antimatter generation. Collaboration between nations and institutions could help address the infrastructure gap. By pooling resources and expertise, countries could share the costs and knowledge required to develop advanced antimatter production facilities. This cooperative approach can accelerate progress and promote innovation in the field. Moreover, establishing a dedicated network of research facilities focused on antimatter could lead to significant breakthroughs. Such infrastructure would allow for more efficient experiments and the sharing of findings across institutions. By fostering an environment conducive to collaboration, the scientific community could make substantial strides in antimatter research. Investments in technology for antimatter production infrastructure could also have broader implications. The advancements developed for antimatter applications might find utility in other areas of science and industry. This potential for cross-disciplinary benefits can make the case for investing in the necessary infrastructure more compelling. Innovative designs and concepts are emerging to optimize the infrastructure required for antimatter production. Researchers are exploring new accelerator technologies and techniques to improve efficiency and reduce costs. Implementing these innovations could streamline the establishment of facilities dedicated to large-scale antimatter generation. As the global scientific community becomes increasingly aware of the potential of antimatter, calls for improved infrastructure are growing. Policymakers and funding agencies are being urged to recognize the importance of developing production capabilities. This shift in perception can lead to increased support for infrastructure projects focused on antimatter research. The collaboration between academia, industry, and government can play a pivotal role in overcoming infrastructure challenges. By working together, stakeholders can identify effective solutions to the logistical and financial hurdles associated with large-scale antimatter production. This united effort could pave the way for a new era in antimatter research and applications. The future of antimatter hinges on the ability to build the necessary infrastructure for its production. Without these advancements, the remarkable potential of antimatter may remain untapped. Focusing on developing a comprehensive framework for antimatter generation is crucial for unlocking its possibilities in energy and propulsion. Safety issues during antimatter production are a critical concern that cannot be overlooked. Given the volatile nature of antimatter, even a tiny amount can lead to catastrophic consequences if not handled properly. Therefore, rigorous safety protocols must be established to ensure the well-being of researchers and the integrity of the facilities. One of the primary risks associated with antimatter production is the potential for accidental annihilation. When antimatter comes into contact with regular matter, the resulting reaction can release an enormous amount of energy in the form of gamma rays. This release poses a serious threat, necessitating the development of secure containment systems to prevent any unwanted interactions. In addition to the risk of annihilation, the production process itself involves high-energy collisions that can generate hazardous byproducts. These byproducts can include radiation and other energetic particles, which can be harmful to personnel working in the vicinity. Comprehensive radiation safety measures are essential to protect researchers from exposure to these dangers. Creating a safe working environment for antimatter production also requires specialized equipment and training. Researchers must be equipped with advanced protective gear and tools designed specifically for handling antimatter safely. Training programs focused on the unique risks of antimatter research are vital to ensure that all personnel are prepared to respond effectively to emergencies. Monitoring systems play a crucial role in maintaining safety during antimatter production. Continuous monitoring of radiation levels and containment systems can provide early warnings of potential issues. Implementing real-time data analysis can help researchers quickly identify and mitigate any risks that may arise during the production process. Emergency response protocols are another key aspect of safety in antimatter facilities. In the event of an accidental release or containment failure, having well-defined procedures can help minimize damage and ensure the safety of personnel. Regular drills and simulations can prepare researchers for potential emergencies and enhance their ability to react swiftly and effectively. Collaboration with safety regulatory bodies is essential for developing robust safety standards in antimatter research. Engaging with organizations that specialize in nuclear safety can provide valuable insights and guidance. These collaborations can lead to the establishment of best practices that are critical for ensuring the safety of antimatter production. Furthermore, the design of antimatter production facilities must prioritize safety from the outset. Architects and engineers should incorporate safety features, such as blast shields and secure storage areas, into the facility layout. By considering safety in the design phase, potential hazards can be mitigated before operations begin. The international nature of antimatter research calls for standardized safety regulations across borders. Harmonizing safety protocols can facilitate collaboration between countries and institutions engaged in antimatter studies. This global approach ensures that best practices are shared and implemented widely, enhancing overall safety in the field. Despite the inherent risks, researchers are committed to advancing antimatter science safely. Ongoing safety research and technological innovations can help improve the practices surrounding antimatter production. As the field evolves, ensuring the safety of personnel and facilities will remain a top priority. Awareness of the safety issues surrounding antimatter production is essential for gaining public support for research initiatives. By demonstrating a commitment to safety and transparency, researchers can foster trust and understanding among the general public. Engaging with communities and stakeholders can help build a solid foundation for future advancements in antimatter applications. In summary, addressing safety issues during antimatter production is crucial for the responsible advancement of this field. By implementing rigorous protocols, investing in training, and fostering collaboration, researchers can work towards a future where antimatter can be safely harnessed for energy and exploration. The journey towards effective antimatter utilization begins with a firm commitment to safety. The availability of resources is a critical factor influencing the future of antimatter production. Creating antimatter requires not only advanced technology, but also access to rare materials that can facilitate the necessary high-energy collisions. The limited supply of these resources can significantly impact research and development efforts in this field. Particle accelerators, essential for producing antimatter, rely on specific components that may not be readily available. For instance, superconducting materials are crucial for creating powerful magnets used in these accelerators. Any scarcity or difficulty in sourcing these materials can delay projects and increase costs. Additionally, the infrastructure required for antimatter research often demands substantial financial investments. Funding for such complex facilities is limited, which can hinder the expansion of research programs. As scientists strive to push the boundaries of antimatter applications, the availability of financial resources remains a pivotal concern. The human resource aspect also plays a vital role in advancing antimatter research. Skilled scientists and engineers are necessary to operate sophisticated equipment and conduct experiments. A shortage of trained professionals in this niche area can slow down progress and limit the potential for innovation. Access to collaboration opportunities is another critical resource for researchers. International partnerships can provide additional expertise, funding, and shared facilities, allowing teams to overcome individual limitations. Establishing these collaborative networks is essential for enhancing the overall capability of antimatter research. Energy resources are also significant, as producing antimatter is an energy-intensive process. The electricity required to power particle accelerators and associated systems is substantial, impacting operational costs. As researchers explore antimatter production, finding sustainable and cost-effective energy sources becomes increasingly important. Moreover, advancements in technology can lead to more efficient use of existing resources. Innovations in accelerated design and material science may allow for reduced consumption of scarce materials. By optimizing processes, researchers can stretch their available resources further, enhancing production capabilities. As competition for research funding intensifies, universities and institutions are seeking creative solutions to resource challenges. Many are exploring public-private partnerships to access additional funding streams. By diversifying their resource base, they can better support ongoing antimatter research initiatives. Public interest in antimatter also plays a role in resource availability. Increased awareness and excitement about the potential applications of antimatter can drive funding and support from both government and private sectors. Engaging the public can create a favorable environment for securing the resources needed for further exploration. The complexity of antimatter research necessitates a holistic approach to resource management. Coordinating efforts across institutions and countries can lead to more efficient use of materials and funding. This collaborative mindset can ensure that researchers are better equipped to tackle the challenges of antimatter production. As the scientific community continues to explore the mysteries of antimatter, the availability of resources will remain a pivotal aspect of progress. Addressing these challenges head-on is essential for realizing the potential of antimatter in energy and propulsion. With thoughtful planning and collaboration, researchers can create a sustainable pathway for advancing antimatter research. The exploration of antimatter is a multifaceted endeavor that requires not just technological advancements, but also a comprehensive approach to resource management. By focusing on the availability of essential resources, researchers can pave the way for significant breakthroughs in the field. Antimatter containment techniques are critical for ensuring the safe handling of this volatile substance. Due to antimatter's propensity to annihilate upon contact with regular matter, specialized methods are necessary to isolate it effectively. Researchers are exploring various strategies to keep antimatter stable and prevent any unwanted interactions. One common approach involves the use of electromagnetic fields to create magnetic traps. These traps utilize powerful magnets to hold antiparticles in place, preventing them from coming into contact with the walls of their containment vessel. This method is essential for storing antimatter for any duration, as it eliminates direct contact with matter. Another technique involves the use of vacuum systems to create an environment devoid of matter. By maintaining a vacuum, researchers can reduce the likelihood of antimatter particles encountering regular matter. This technique complements magnetic trapping and enhances the overall safety of antimatter storage. Cryogenic technology is also being investigated as a means of containment. By cooling materials to extremely low temperatures, researchers can reduce the energy of particles, thus minimizing the chances of unwanted interactions. This approach aims to create an optimal environment for holding antimatter while maintaining its stability. Innovations in materials science are contributing to the development of better containment systems. Researchers are exploring advanced materials that can withstand the extreme conditions required for antimatter storage. These materials must be both lightweight and durable to ensure effective containment without adding significant weight to storage systems. The use of laser technology is another promising avenue for antimatter containment. Lasers can manipulate and cool antiparticles, allowing researchers to maintain better control over their movements. This precision can enhance the effectiveness of existing containment techniques and open up new possibilities for storing antimatter. In addition to physical containment, researchers are also examining the theoretical aspects of antimatter behavior. Understanding how antimatter interacts with electromagnetic fields and other forces is essential for improving containment methods. These insights can inform the design of more effective storage systems that minimize risk. Real-time monitoring of containment systems is crucial for ensuring safety. Continuous observation allows researchers to detect any deviations or potential breaches in the containment setup. Implementing advanced sensors and data analysis can enhance the overall reliability of antimatter storage solutions. Collaborative efforts among international research institutions are also leading to advancements in containment techniques. By sharing knowledge and resources, scientists can develop innovative solutions that address common challenges. This collaborative approach fosters a community focused on improving safety and efficiency in antimatter research. Training and education are vital components of effective antimatter containment. Researchers must be well versed in the principles of antimatter behavior and the technologies used for containment. Providing thorough training ensures that all personnel involved in antimatter research are prepared to handle it safely and responsibly. The combination of various containment techniques can create a more robust storage solution. By integrating magnetic traps, vacuum systems, and cryogenic technology, researchers can develop comprehensive strategies for antimatter containment. This multifaceted approach enhances the likelihood of successful storage and handling. As advancements in antimatter research continue, the evolution of containment techniques will be crucial. Ongoing exploration of new methods and materials will pave the way for safer and more effective storage solutions. The quest for reliable antimatter containment remains a fundamental aspect of harnessing its potential in energy and propulsion. Magnetic traps play a crucial role in the containment of antimatter, but they come with several challenges that researchers must overcome. One significant issue is the need for extremely strong and stable magnetic fields to effectively hold antimatter particles in place. If these fields fluctuate or weaken, the particles may escape and come into contact with regular matter, leading to annihilation. Achieving the necessary strength in magnetic fields requires sophisticated technology and precise calibration. The magnets used in these traps must be powerful enough to counteract the natural motion of antiparticles. Maintaining this level of strength consistently over time can be a daunting task for researchers. Another challenge lies in the design of the magnetic trap itself. Creating a configuration that can effectively contain various types of antiparticles while minimizing energy loss is complex. The geometry of the trap must be carefully optimized to ensure that particles remain stable and do not drift out of the designated containment area. Thermal effects also pose challenges in magnetic trapping. When antimatter is produced, it can generate heat, which may affect the stability of the magnetic fields. Researchers must find ways to manage this heat to maintain effective containment without compromising the integrity of the trapping system. The interaction of antimatter with its surrounding environment can complicate magnetic trapping efforts. Any stray electromagnetic fields or charged particles in the vicinity can disrupt the magnetic trap's effectiveness. Isolating the trap from external influences is essential for maintaining a controlled environment for antimatter containment. Limited lifetimes of antiparticles can further hinder magnetic trapping efforts. Antiparticles tend to decay or annihilate quickly if not contained properly. Researchers must develop methods to create and store antimatter efficiently before the particles have a chance to dissipate. Precision in the alignment of magnetic fields is vital for effective trapping. Even slight misalignments can lead to instability, allowing antiparticles to escape. Continuous monitoring and adjustments are necessary to ensure that the magnetic fields remain optimally configured. Energy consumption is another concern related to magnetic traps. Producing and maintaining strong magnetic fields can require significant amounts of energy. Finding ways to reduce energy consumption while still achieving effective containment remains a key challenge for researchers. The scalability of magnetic trapping systems is also an important consideration. While small-scale traps can be developed for experimental purposes, scaling these systems up for practical applications can be complex, researchers are exploring strategies to create larger magnetic traps that can hold more antimatter without compromising stability. Collaboration between physicists, engineers, and material scientists is essential for addressing the challenges of magnetic traps. By combining expertise from different fields, researchers can develop innovative solutions to improve the design and effectiveness of these containment systems. This interdisciplinary approach fosters advancements that may lead to breakthroughs in antimatter research. The ongoing exploration of alternative magnetic trapping techniques is another avenue for overcoming existing challenges. Researchers are investigating novel configurations and materials that could enhance the stability and efficiency of magnetic traps. These innovations could ultimately improve the feasibility of using magnetic traps for practical antimatter applications. As scientists continue to tackle the challenges associated with magnetic traps, the potential for effective antimatter containment remains promising. Each advancement in technology and design brings us closer to overcoming these obstacles. The pursuit of reliable magnetic trapping methods is essential for harnessing the power of antimatter in future energy solutions and propulsion systems. Long-term storage of antimatter presents a series of complex challenges that researchers must navigate. One of the primary concerns is the instability of antimatter particles, which can lead to rapid annihilation if not properly contained. Ensuring the safe storage of antimatter over extended periods is essential for any future applications. The current methods of antimatter storage often involve magnetic traps or vacuum systems, but these solutions can be limited in their effectiveness for long-term containment. Over time, the potential for small fluctuations in the containment environment can increase the risk of particle escape. This unpredictability complicates efforts to maintain stable storage conditions. Energy loss is another critical issue associated with long-term storage. As antimatter is stored, there can be gradual energy dissipation, which may affect the particle's stability. Researchers need to develop techniques that minimize energy loss to ensure that antimatter remains viable for extended periods. In addition, the materials used for containment systems must be resistant to the unique challenges posed by antimatter. Conventional materials may not withstand the extreme conditions associated with antimatter storage. Identifying advanced materials that can endure these environments is vital for improving long-term storage solutions. Another challenge is the potential degradation of storage systems over time. Continuous exposure to the intense electromagnetic fields required for containment may cause wear and tear on the materials used. Ensuring the durability and longevity of these systems is crucial for maintaining effective long-term storage. Moreover, safety considerations become increasingly important with long-term storage. As antimatter is stored for longer periods, the risk associated with potential accidents or breaches in containment increases. Establishing robust safety protocols is essential to mitigate these risks and protect both personnel and facilities. The complexity of monitoring stored antimatter over extended periods also poses challenges. Continuous observation of containment conditions is necessary to ensure stability, but implementing reliable monitoring systems can be technically demanding. Developing advanced sensors that can function effectively in storage environments is essential for long-term safety. Collaborative research efforts can enhance the understanding of long-term storage issues. By pooling knowledge from various fields, researchers can identify innovative approaches to overcome the challenges associated with storing antimatter. This collaborative spirit is crucial for developing comprehensive strategies that address the multifaceted nature of antimatter storage. As research progresses, scientists are exploring alternative methods for long-term storage. Some are investigating cryogenic techniques, which could potentially enhance the stability of stored antimatter. By lowering the temperature of the storage environment, researchers may be able to minimize particle motion and improve containment. The financial implications of long-term antimatter storage cannot be ignored. The costs associated with maintaining advanced containment systems over time can be substantial. Addressing these financial challenges is vital for ensuring that antimatter research remains sustainable and viable in the long run. Public perception of antimatter also influences long-term storage efforts. Concerns about safety and the potential for accidents may impact funding and support for antimatter research. Engaging with the public to explain the safety measures and benefits of antimatter research is essential for garnering broader support. Finally, The future of antimatter storage will depend on ongoing innovations in science and technology. As researchers continue to develop new methods and materials, the possibilities for safe and effective long-term storage expand. The quest for reliable containment solutions is a crucial step toward unlocking the potential of antimatter in energy and space exploration. Energy losses during the containment of antimatter pose significant challenges for researchers. As antimatter is stored, there is a tendency for the particles to lose energy over time, which can lead to instability. Addressing these energy losses is crucial for maintaining the integrity of the containment system. One primary source of energy loss is thermal radiation. Even in well-designed magnetic traps or vacuum environments, heat can gradually dissipate into the surroundings. This thermal leakage can undermine the stability of stored antimatter, making it imperative to develop systems that minimize heat transfer. Another factor contributing to energy losses is the interaction between antimatter and the materials used in containment. The presence of ordinary matter, even in small amounts, can absorb energy from the antimatter particles. Ensuring that containment materials are optimized to reduce these interactions is essential for preserving energy. In addition, fluctuations in the magnetic fields can also lead to energy dissipation. If the strength of the magnetic fields wavers, it can cause antiparticles to move unpredictably, resulting in energy loss. Researchers must focus on stabilizing these fields to maintain a consistent containment environment. Cryogenic techniques are being explored as a way to mitigate energy losses. By cooling the containment environment, researchers hope to slow down particle motion and reduce thermal energy dissipation. This method could provide a more stable storage solution for antimatter. The design of the containment system itself can influence energy retention. Innovative engineering approaches that minimize energy pathways can help maintain the stored energy of antimatter. These designs may include advanced insulating materials and configurations that optimize the containment structure. Monitoring energy levels during containment is another vital aspect of ensuring stability. Continuous observation of particle energy can provide insights into potential losses and help researchers make necessary adjustments. Implementing sophisticated monitoring systems is crucial for maintaining effective containment. Another challenge is the overall efficiency of the containment technology. Current methods may not fully capitalize on the energy potential of antimatter, leading to wastage. Exploring new containment technologies that enhance energy retention will be essential for the future of antimatter research. Long-term predictions of energy retention also require detailed modeling and simulations. By creating accurate models of antimatter behavior in containment systems, researchers can better understand how energy losses occur. These predictive tools can aid in developing strategies to minimize losses over time. Public engagement regarding energy losses in antimatter containment is important for building trust in research efforts. Explaining the complexities of energy retention and the measures taken to address these challenges can foster greater understanding. This transparency is essential for gaining support for ongoing antimatter research initiatives. Addressing energy losses in containment is not merely a technical challenge. It's fundamental to realizing the potential of antimatter as an energy source. Each advancement in containment technology that reduces energy losses brings us closer to practical applications. As scientists continue to innovate, the possibilities for effectively harnessing antimatter energy will expand. By focusing on minimizing energy losses during containment, researchers can enhance the overall viability of antimatter applications. Continuous exploration of new methods and technologies will be key to overcoming these challenges. The journey towards effective antimatter energy solutions is filled with opportunities for groundbreaking discoveries. Recent breakthroughs in containment technology are opening new avenues for safely storing antimatter. Innovative designs are being developed that enhance the stability of magnetic traps, allowing for more effective control over antiparticles. These advancements are crucial for paving the way toward practical applications of antimatter. One promising approach involves the use of advanced superconducting materials to create stronger magnetic fields. By utilizing these materials, researchers can produce more stable and efficient containment systems. This improvement minimizes energy losses and helps maintain the necessary conditions for antimatter storage. Another significant development is the integration of automated monitoring systems into containment facilities. These systems continuously track the conditions within the containment environment, providing real-time data on stability and energy levels. Such automation allows for immediate adjustments to be made, enhancing the overall effectiveness of the storage solution. Researchers are also exploring the use of advanced computational models to simulate antimatter behavior in containment. By creating detailed simulations, scientists can predict how antimatter will interact with various containment materials and configurations. These insights guide the design of more effective storage systems and help identify potential weaknesses. The application of cryogenic technology is proving to be a game-changer in antimatter containment. By cooling the containment environment to extremely low temperatures, researchers can significantly reduce thermal energy dissipation. This method helps maintain the stability of stored antimatter over longer periods, making it a viable option for future applications. In addition, new materials are being developed specifically for antimatter containment. These materials are engineered to minimize energy absorption and withstand the harsh conditions associated with antimatter storage. As these materials are refined, they may revolutionize how antimatter is contained and handled. Collaborative efforts between universities, research institutions, and private companies are driving innovation in containment technology. By combining expertise and resources, teams can tackle complex challenges more effectively. This collaborative approach fosters a culture of innovation that is essential for advancing antimatter research. Innovations in laser technology are also being integrated into containment systems. Lasers can manipulate and cool antiparticles, allowing for precise control over their movements. This enhanced control can lead to more effective containment strategies and reduce the risk of accidental annihilation. Moreover, the exploration of hybrid containment systems is gaining traction. These systems combine multiple techniques, such as magnetic traps and vacuum environments, to create more robust storage solutions. By integrating various technologies, researchers can enhance the overall reliability of antimatter containment. Research into the scalability of containment technologies is also underway. Developing larger systems capable of storing greater quantities of antimatter could significantly impact potential applications in energy and propulsion. Scaling up these technologies will be essential for realizing the full potential of antimatter as a resource. Emerging breakthroughs in nanotechnology are contributing to the advancement of containment solutions. Utilizing nanoscale materials and devices may enhance the performance of existing containment systems. As this field progresses, it holds the promise of further improving the stability and efficiency of antimatter storage. The ongoing exploration of breakthroughs in containment technology underscores the commitment to safely harnessing antimatter. Each advancement brings researchers closer to overcoming the barriers associated with antimatter storage. The future of antimatter research is promising, driven by innovations that enhance containment capabilities. Space exploration propulsion is an exciting area where antimatter technology holds tremendous promise. The potential to utilize antimatter as a fuel source could revolutionize how we travel beyond our solar system. With the ability to generate immense energy from small amounts of antimatter, spacecraft could achieve unprecedented speeds. One of the primary advantages of antimatter propulsion is its energy density. Just a fraction of a gram of antimatter can produce energy equivalent to several tons of conventional fuel. This extraordinary efficiency could enable missions to distant planets or even neighboring star systems within a human lifetime. Antimatter propulsion systems could significantly reduce travel times compared to current chemical rockets. For example, a spacecraft powered by antimatter could reach Mars in days instead of months. This reduction in travel time not only enhances mission feasibility, but also reduces the risks associated with long-duration space travel. In addition to enhancing speed, antimatter propulsion could also improve maneuverability in space. The high energy output allows for more agile spacecraft that can change direction quickly. This capability is crucial for navigating the complex gravitational fields of planets and asteroids during exploration missions. The concept of antimatter engines is still in the early stages of development, but researchers are actively investigating viable designs. These engines would need to efficiently convert the energy released from antimatter annihilation into thrust. Developing such systems will require extensive research and engineering to ensure safety and effectiveness. Safety remains a paramount concern when considering antimatter propulsion. The destructive potential of antimatter reactions necessitate strict safety protocols and reliable containment systems. Researchers must ensure that these propulsion systems can operate safely, both in the launch phase and during space travel. International collaboration in the field of antimatter propulsion can accelerate progress. By pooling expertise and resources, scientists and engineers from various countries can work together on developing advanced propulsion technologies. This cooperative approach fosters innovation and may lead to breakthroughs that benefit the global space exploration community. The applications of antimatter propulsion extend beyond interplanetary missions. The technology could also facilitate deep space exploration, potentially allowing us to reach other star systems. By reducing travel times, antimatter-powered spacecraft may open new frontiers in our search for extraterrestrial life. Simulations and theoretical models are critical for understanding the dynamics of antimatter propulsion systems. These models can help researchers predict performance under various conditions, guiding the design and optimization of propulsion technologies. Utilizing advanced computational tools will enhance the efficiency of the development process. Investments in research and development for antimatter propulsion are vital for advancing our capabilities in space exploration. Funding from government agencies and private sectors can provide the necessary resources to pursue this ambitious goal. With sustained investment, the dream of antimatter-powered spacecraft could become a reality. The potential for antimatter propulsion aligns with humanity's growing interest in space exploration and discovery. As we look to the stars, the technologies we develop will shape our ability to explore and understand the universe. The pursuit of antimatter propulsion represents a bold step toward realizing these aspirations. The quest for effective antimatter propulsion is not just about technology, it's about expanding our horizons and our understanding of the cosmos. Each advancement brings us closer to harnessing the incredible power of antimatter for exploration. The journey into this realm of space travel is just beginning, filled with possibilities for the future. Antimatter is increasingly being explored as a potential fuel source due to its extraordinary energy density. The annihilation of antimatter with matter releases energy according to Einstein's equation E equals mc squared, showcasing how a small amount of antimatter can produce vast amounts of energy. This unique property positions antimatter as an attractive alternative to conventional fuels. One of the most compelling aspects of antimatter as a fuel source is its efficiency. Unlike chemical fuels, which rely on combustion processes, antimatter reactions produce energy with minimal waste. This efficiency could drastically change the landscape of energy generation, particularly in areas where high energy output is essential. In practical terms, the energy produced by antimatter could revolutionize both space travel and terrestrial applications. For instance, in spacecraft, antimatter propulsion systems could enable rapid travel across vast distances, making interplanetary missions more feasible. The implications for exploration and colonization of other planets are immense. Furthermore, antimatter's energy release is immediate, allowing for rapid thrust generation. This characteristic can significantly enhance maneuverability in space, giving spacecraft the ability to navigate complex gravitational fields effectively. Such responsiveness is critical for missions involving planetary landings or flybys of multiple celestial bodies. While the potential of antimatter as a fuel source is exciting, significant challenges remain in harnessing it effectively. Producing antimatter is an incredibly costly and energy-intensive process, which currently limits its practical use. Addressing these production challenges is essential for unlocking the full potential of antimatter as a viable fuel. Storage and containment of antimatter also present critical hurdles. Since antimatter annihilates upon contact with ordinary matter, developing safe and effective containment systems is vital. Researchers are exploring various techniques to safely store antimatter until it can be utilized, ensuring that no energy is wasted during storage. In addition to space applications, the potential for antimatter energy extends to terrestrial uses. Antimatter could be harnessed in power plants to generate electricity with minimal environmental impact. The possibility of creating clean, efficient energy sources could address many of the pressing energy challenges we face today. The research surrounding antimatter fuel has attracted interest from both public and private sectors. Investments in this area could lead to breakthroughs that make antimatter more accessible as an energy source. Collaboration between governments, academic institutions, and industry players is essential for accelerating research and development. Innovative approaches to antimatter production and utilization are emerging as researchers explore this fascinating field. By leveraging advancements in technology and materials science, scientists are working to improve the efficiency of antimatter generation. These innovations could eventually pave the way for more widespread use of antimatter as a fuel source. Understanding the safety implications of using antimatter as fuel is also critical. As the potential for significant energy release exists, establishing robust safety protocols is necessary to prevent accidents. Researchers are committed to developing guidelines that ensure the safe handling and application of antimatter energy. Public perception plays a crucial role in the development of antimatter as a fuel source. Educating the public about the benefits and challenges associated with antimatter can foster greater acceptance and support for research initiatives. Increased awareness may lead to more funding and resources dedicated to exploring antimatter technologies. The exploration of antimatter as a fuel source represents a frontier in energy science that holds immense possibilities. As researchers continue to investigate this potential, the implications for energy production, space travel, and environmental sustainability become increasingly significant. The journey into the realm of antimatter fuels is just beginning, with the promise of revolutionary advancements on the horizon. The exploration of antimatter technology extends into military applications, where its unique properties could offer significant advantages. The immense energy release from antimatter annihilation could be harnessed for advanced weaponry or propulsion systems. This potential raises important questions about the implications and ethics of using such powerful technology. One potential military application is in the development of propulsion systems for military spacecraft. Antimatter-powered engines could enable faster and more maneuverable vehicles, providing a tactical advantage in space operations. The speed and efficiency of antimatter propulsion could transform how military forces engage in space-related missions. Another area of interest lies in using antimatter for directed energy weapons. These weapons could harness the energy released during antimatter annihilation to create powerful beams capable of incapacitating or destroying targets. The precision and effectiveness of such systems could enhance military capabilities in various scenarios. However, the use of antimatter in military applications poses significant challenges. The production and storage of antimatter are currently expensive and complex, making widespread implementation difficult. Addressing these logistical hurdles will be essential for any military organization considering antimatter technology. Safety is also a critical concern when discussing antimatter's potential in military settings. The destructive power of antimatter reactions necessitates strict controls and safeguards to prevent accidents or misuse. Ensuring that such technology is handled responsibly and securely is crucial for maintaining safety. International regulations regarding the use of antimatter in military applications are still largely undeveloped. As nations explore the potential of this technology, discussions on establishing guidelines and treaties will be essential. Collaborative efforts can help create a framework that addresses safety, ethical concerns, and potential arms races. Research into antimatter's military applications could also foster advancements in other fields. Technologies developed for military purposes often find their way into civilian applications, leading to innovations that benefit society as a whole. Exploring antimatter in a military context could spur breakthroughs that have wider implications for energy and propulsion technologies. Furthermore, the strategic implications of antimatter technology cannot be overlooked. Nations that develop effective antimatter applications may gain significant leverage in geopolitical dynamics. This potential for disruption underscores the importance of monitoring advancements in antimatter research globally. Investments in antimatter research from military organizations could catalyze progress in containment and production technologies. By focusing on the unique challenges associated with antimatter, military funding may lead to breakthroughs that benefit both defense and civilian sectors. This dual-use potential can be a driving force behind further exploration of antimatter applications. The conversation surrounding antimatter in military contexts also encompasses ethical considerations. The potential for powerful antimatter weapons raises questions about the morality of developing such capabilities. Engaging in dialogues about these ethical implications is essential to navigate the complexities of antimatter technology responsibly. Public awareness of the military applications of antimatter is vital for informed discussions about its use. educating citizens on the potential benefits and risks can foster a more nuanced understanding of the technology. This engagement can encourage transparency and accountability in the development and deployment of antimatter technologies. As research progresses, the future of antimatter in military applications remains an area of intense interest. While the challenges are significant, the potential rewards could reshape military strategies and capabilities. The exploration of antimatter technology will undoubtedly continue to spark debate and innovation in both military and civilian domains. The potential of antimatter in energy grids is an exciting area of research that could revolutionize how we generate and distribute power. Due to its incredibly high energy density, antimatter could provide a compact and efficient energy source for future energy systems. This capability might lead to significant reductions in the reliance on traditional fossil fuels. Utilizing antimatter in energy grids could allow for the generation of electricity with minimal environmental impact. The annihilation process releases energy without producing harmful emissions, making it a cleaner alternative to conventional energy sources. This aspect aligns with global efforts to transition to more sustainable energy solutions. One possible application is the development of antimatter reactors that could supply power to cities or industries. These reactors would harness the energy released from antimatter annihilation to generate electricity efficiently. The compact nature of antimatter could enable localized energy production, reducing the need for extensive transmission infrastructure. Antimatter's potential for energy storage is also noteworthy. The ability to store energy in antimatter form could offer a way to balance supply and demand in energy grids. By converting surplus energy into antimatter, systems could tap into this stored energy during peak demand periods, providing a reliable power source when needed. Research into the integration of antimatter into existing energy grids is ongoing. Scientists are investigating how antimatter energy systems can complement or enhance current infrastructure. By exploring synergies between antimatter and renewable sources like solar and wind, researchers aim to create a more resilient energy ecosystem. One significant challenge is the cost associated with producing antimatter. The current production methods are energy-intensive and expensive, making it difficult to compete with established energy sources. Finding ways to reduce the costs of antimatter generation will be crucial for unlocking its potential in energy grids. Safety and regulatory considerations must also be addressed as antimatter technologies develop. Ensuring that antimatter energy systems operate safely within energy grids is essential for public acceptance and trust. Developing comprehensive safety protocols and regulations will be key to integrating antimatter into mainstream energy applications. The potential for international collaboration in developing antimatter energy grid systems is vast. By sharing knowledge and resources, countries can work together to explore the feasibility and practicality of antimatter technologies. This collaboration can accelerate advancements and create a global network focused on sustainable energy solutions. Additionally, the scalability of antimatter systems is an important factor to consider. As research progresses, scientists must determine how to implement antimatter energy solutions on a larger scale. Developing technologies that can handle increased production and distribution while maintaining safety will be essential. The implications of harnessing antimatter for energy grids extend beyond power generation. The integration of such technologies could influence energy policies and drive innovation in other sectors. By redefining how we produce and consume energy, antimatter could lead to broader economic and social changes. Public interest in antimatter as an energy source is essential for fostering support for research initiatives. Engaging communities and stakeholders can promote awareness of the benefits and potential challenges associated with antimatter energy systems. This dialogue is crucial for building momentum toward the development of antimatter technologies. As scientists continue to explore the energy grid potential of antimatter, the future looks promising. With advancements in technology and a commitment to sustainability, antimatter could become a key player in global energy strategies. The journey toward integrating antimatter into energy grids is an exciting frontier that holds immense possibilities for the future. Powering deep space colonies with antimatter presents a fascinating opportunity for sustainable human habitation beyond Earth. The immense energy density of antimatter makes it an ideal candidate for supporting the life support systems and infrastructure needed in these remote environments. By utilizing antimatter, colonies could operate independently and efficiently for extended periods. Antimatter-powered systems could ensure a consistent energy supply, essential for various colony functions, including agriculture, manufacturing, and communication. This reliability is crucial when considering the challenges of resupplying distant colonies from Earth. The ability to generate power on-site using antimatter could significantly enhance self-sufficiency. The compact nature of antimatter systems allows for efficient energy storage and distribution. With smaller energy footprints, these systems could be integrated into the design of colony habitats, minimizing the space required for power generation. This optimization would enable colonies to allocate more resources toward essential activities and technologies. In addition to providing power for everyday needs, antimatter can also fuel advanced technologies within deep space colonies. For instance, propulsion systems powered by antimatter could enable faster travel between different locations in space. This capability would facilitate exploration and expansion efforts for colonists, allowing them to reach new worlds more efficiently. Safety is a paramount consideration when implementing antimatter systems in deep space colonies. The potential risks associated with antimatter must be thoroughly understood and addressed. Developing robust safety protocols and containment measures will be essential to ensure the well-being of colony inhabitants. Research into the feasibility of antimatter as a power source for deep space colonies is ongoing. Scientists are working to identify the technical and logistical challenges associated with this technology. By exploring the potential applications of antimatter in these environments, researchers aim to pave the way for future colonization efforts. Collaboration between various scientific disciplines will play a critical role in advancing antimatter technology for colonization. Engineers, physicists, and biologists must work together to create systems that are not only efficient, but also conducive to human life. This interdisciplinary approach will enhance the overall design and functionality of antimatter-powered colonies. Additionally, the development of closed-loop systems powered by antimatter could support life in harsh space environments. These systems would recycle resources while providing energy, promoting sustainability within the colony. The integration of antimatter technology can lead to more resilient ecosystems that thrive in the depths of space. The potential for antimatter to power deep space colonies also highlights the importance of research funding and investment. Government and private sector support will be crucial in advancing this technology and addressing its challenges. As interest in space exploration grows, securing financial resources for antimatter research will become increasingly vital. Engaging the public in discussions about the possibilities of antimatter in deep space colonization can foster greater support for research initiatives. Raising awareness of the potential benefits and challenges can lead to informed discussions and encourage investment. Public interest in these advancements can drive the development of technologies that enable human settlement beyond Earth. The exploration of antimatter as a power source for deep space colonies aligns with humanity's aspirations for space exploration. The pursuit of sustainable energy solutions in extraterrestrial environments is a bold step toward realizing our potential as a multiplanetary species. As scientists continue to investigate the applications of antimatter, the dream of colonizing other worlds becomes more achievable. By harnessing the power of antimatter, we may unlock new possibilities for human habitation in space. Each advancement in technology brings us closer to a future where deep space colonies can thrive. The journey into this realm of exploration is just beginning, filled with exciting prospects for the future of humanity and the cosmos. The current cost of producing antimatter is staggering, with estimates placing it around $62.5 trillion per gram. This astronomical figure primarily reflects the complexities and energy demands of creating antimatter in laboratories. The high expense poses significant barriers to its practical applications, limiting its use to experimental research. The production of antimatter typically occurs in particle accelerators, which collide high-energy particles to generate antiparticles. The process is not only energy-intensive, but also yields only minuscule amounts of antimatter at a time. This low output further drives up the cost, making it one of the most expensive substances on Earth. To put this into perspective, the price of antimatter dwarfs that of gold, which is already considered a precious metal. The sheer cost makes it impractical for large-scale applications, whether in energy generation, propulsion, or other potential uses. As a result, antimatter remains confined to specialized research environments, rather than mainstream use. The energy required to produce even a tiny fraction of a gram of antimatter is immense. Current technologies consume vast amounts of electricity and resources to achieve the necessary conditions for antimatter creation. This inefficiency contributes to the overall high cost, as the energy input often exceeds the potential energy that could be extracted from the antimatter. Efforts to reduce the cost of antimatter production are ongoing within the scientific community. Researchers are exploring innovative methods to enhance production efficiency, such as improving particle accelerator designs or developing alternative generation techniques. Success in this area could lead to breakthroughs that significantly lower the cost per gram. In addition, advancements in technology may pave the way for new, cost-effective production methods. For example, exploring cosmic ray interactions or utilizing laser-based systems could potentially yield antimatter at lower costs. By diversifying production techniques, scientists hope to make antimatter more accessible for various applications. International collaborations are also vital in addressing the high cost of antimatter production. By pooling resources and sharing knowledge, research institutions can tackle the challenges associated with creating antimatter. These partnerships may lead to innovations that enhance efficiency and lower production costs. The economic implications of reducing the cost of antimatter are profound. If antimatter could be produced at a fraction of its current price, it might open new avenues in energy production, space travel, and medical applications. This shift would not only change the landscape of scientific research, but could also have broader impacts on society. Public interest and investment in antimatter research could drive advancements toward reducing production costs. As awareness of the potential benefits grows, funding may increase to support innovative projects focused on antimatter. Engaging stakeholders in discussions about the future of antimatter can foster a more supportive environment for research. The high cost of antimatter production serves as a reminder of the complexities involved in unlocking its potential. As researchers work tirelessly to develop more efficient methods, the hope remains that these efforts will eventually lead to practical applications. The journey toward affordable antimatter is challenging, yet the rewards could be transformative. While the current price per gram of antimatter is prohibitive, the ongoing research and development efforts signal a commitment to overcoming these obstacles. Scientists remain optimistic that advancements in technology and collaborative initiatives will lead to breakthroughs. The potential of antimatter as a valuable resource continues to inspire exploration and innovation. The pursuit of reducing antimatter costs reflects a broader ambition to expand humanity's horizons in energy and exploration. Each step forward in this research brings us closer to realizing the extraordinary possibilities that antimatter offers. As the scientific community continues to innovate, the dream of harnessing antimatter could one day become a reality. Economic scaling challenges present significant obstacles to the widespread application of antimatter technology. The current production methods are limited in both efficiency and output, making it difficult to meet the demands of large-scale applications. As researchers aim to transition from experimental to practical use, these economic hurdles must be addressed. One major issue is the high cost associated with antimatter production, which significantly hampers scalability. Existing facilities are primarily designed for small-scale research, rather than mass production, leading to limited quantities of antimatter generated. This discrepancy creates a gap between supply and potential demand, making large-scale deployment economically unfeasible. The infrastructure required to produce antimatter on a larger scale is both expensive and complex. Building new facilities equipped with advanced particle accelerators entails substantial financial investment and technical expertise. Securing funding for such large-scale projects can be challenging, especially in a competitive research landscape. Furthermore, the technology needed to improve the efficiency of antimatter production is still under development. Enhancing production methods to lower costs and increase output will be essential for overcoming economic scaling challenges. Research efforts must focus on innovative techniques that can lead to more effective and affordable antimatter generation. The energy consumption associated with antimatter production also plays a role in the economic viability of scaling up. Producing even a tiny amount of antimatter requires vast amounts of energy, which adds to overall costs. Finding ways to reduce energy consumption while maintaining production efficiency will be critical for future advancements. Additionally, the existing workforce may not be adequately prepared for large-scale antimatter production. Specialized training in the necessary technologies and safety protocols is essential to ensure that personnel can operate effectively in new facilities. Developing training programs to build a skilled workforce is a crucial step in overcoming scaling challenges. International collaborations could play a vital role in addressing these economic scaling issues. By pooling resources and expertise, countries can work together to develop more efficient production methods and share the financial burden. Collaborative efforts can accelerate progress and lead to breakthroughs that might not be possible in isolated research environments. Another consideration is the regulatory framework surrounding antimatter production. The lack of established guidelines and policies can create uncertainty for potential investors and researchers. Developing a clear regulatory landscape will be important for fostering confidence in antimatter technologies and encouraging investment. Public perception of antimatter technology can also impact its economic scaling. Concerns about safety and practicality may deter funding and support for research initiatives. Engaging the public through education and outreach can help alleviate fears and promote understanding of the potential benefits of antimatter applications. The market demand for antimatter technologies is still largely untested. While the potential applications are numerous, such as in energy generation and propulsion, realizing that demand requires significant advancements in production capabilities. Identifying and promoting specific use cases can help drive interest and investment in antimatter research. As researchers work to overcome the economic scaling challenges associated with antimatter, the importance of innovation cannot be overstated. Each advancement in production technology can contribute to making antimatter more accessible for various applications. The pursuit of solutions to these challenges is essential for unlocking the potential of antimatter as a transformative resource. In summary, addressing economic scaling challenges is crucial for realizing the promise of antimatter technology. Through collaborative efforts, innovative solutions, and public engagement, researchers can pave the way for broader applications of antimatter. The future of antimatter research depends on overcoming these hurdles and advancing the technology to a point of practical use. The future cost reduction potential of antimatter production is an area of active exploration and optimism within the scientific community. As technology advances, researchers are hopeful that innovations will lead to more efficient methods of generating antimatter. This shift could dramatically decrease the current astronomical costs associated with production. One promising avenue for cost reduction involves improving particle accelerator designs. Next-generation accelerators may offer enhanced energy efficiency and increased output of antimatter. By optimizing the performance of these facilities, scientists aim to produce larger quantities of antimatter at a fraction of the current price. The exploration of alternative production techniques is also gaining traction. For instance, using laser-based systems or exploiting natural cosmic ray interactions could provide new pathways for generating antimatter. These innovative methods may not only lower cost but also enhance the overall efficiency of antimatter production. Materials science plays a crucial role in future cost reduction efforts. Developing advanced materials that can withstand the demands of antimatter production could improve system performance and longevity. As new materials are discovered and engineered, they may facilitate more cost-effective containment and generation processes. Collaborative research initiatives across institutions and countries can further drive down costs. By pooling resources and expertise, researchers can tackle the challenges associated with antimatter production more effectively. This teamwork can lead to the development of shared technologies that benefit multiple projects simultaneously. Investments in automation and artificial intelligence are another potential game-changer for reducing costs. Implementing these technologies can streamline production processes and minimize human error. The increased efficiency could significantly cut down on the time and resources needed for antimatter generation. Long-term research and development strategies focused on antimatter technology are essential. By committing to sustained funding and innovation, the scientific community can work toward more sustainable production methods. This dedication will be vital for achieving the breakthroughs necessary to make antimatter more economically viable. Public and private sector partnerships may also play a critical role in facilitating cost reductions. By combining the resources of government agencies with the agility of private companies, researchers can expedite advancements in antimatter technology. This collaborative approach can help bridge the gap between theory and practical applications. A greater understanding of the underlying physics governing antimatter production can lead to further efficiencies. Ongoing research into particle interactions and containment methods can yield insights that enhance production techniques. As our knowledge expands, so too does the potential for reducing the costs associated with antimatter generation. The potential for economies of scale is another aspect to consider. As production methods improve and become more efficient, larger facilities may be developed that can produce antimatter at reduced costs. This scalability can create a more sustainable model for antimatter generation, making it more accessible for various applications. Training the next generation of scientists and engineers will be critical for realizing cost reduction potential. By equipping new researchers with the skills necessary to innovate in the field, we can foster an environment of creativity and advancement. This investment in education will be essential for developing the solutions needed to overcome current economic barriers. Ultimately, the future of antimatter production depends on a combination of technological advancements, collaborative efforts, and sustained investment. Each step forward in reducing costs can bring us closer to harnessing antimatter for practical applications. The promise of antimatter as a valuable resource remains alive, driven by the pursuit of innovation and efficiency. The market demand for antimatter energy is a subject of increasing interest as scientists explore its potential applications. As global energy needs continue to rise, there is a growing search for more efficient and sustainable energy sources. Antimatter, with its remarkable energy density, could provide a solution that meets these escalating demands. Interest in antimatter energy is not limited to the scientific community. Various industries are also beginning to recognize its potential. Sectors such as aerospace and defense are particularly intrigued by the applications of antimatter propulsion systems. The ability to achieve faster and more efficient travel could revolutionize space exploration and military capabilities. The medical field may also contribute to the demand for antimatter energy. Positron emission tomography, or PET scans, already utilizes antimatter principles for diagnostic imaging. As researchers develop new applications, the potential for antimatter to enhance medical technologies could drive further interest and investment in this area. Another factor influencing market demand is the global push for clean energy alternatives. As countries strive to reduce their carbon footprints, the search for non-polluting energy sources intensifies. Antimatter energy could provide a way to generate electricity without harmful emissions, making it an attractive option for environmentally conscious markets. The potential for antimatter to power deep space colonies and facilitate interplanetary travel is also fueling interest. As space exploration becomes a more prominent goal for nations and private companies, the need for efficient energy sources increases. Antimatter could enable sustainable human habitation on other planets, further driving demand for its applications. Government funding and policy support are crucial for stimulating market demand for antimatter energy. Investments in research and development can accelerate the technological advancements needed to make antimatter a viable energy source. Public policies that promote clean energy initiatives can also create a favorable environment for antimatter technologies. However, the current high costs associated with antimatter production remain a significant barrier to market entry. Until production methods become more efficient and affordable, widespread adoption will be challenging. Addressing these economic hurdles will be essential for realizing the full potential of antimatter energy in various markets. The collaboration between academia, industry, and government can play a pivotal role in driving demand for antimatter technologies. By working together, these sectors can create pathways for innovation and investment that benefit all parties involved. This synergy can help translate research breakthroughs into practical applications that meet market needs. As public interest in space exploration and clean energy grows, so too does the potential for antimatter energy. Engaging the public through educational initiatives and outreach programs can foster a better understanding of antimatter's benefits. This awareness can translate into increased support for research funding and policy initiatives. The evolving landscape of energy markets presents an opportunity for antimatter to carve out a niche. As technology advances, the feasibility of using antimatter for practical energy solutions may become more apparent. Identifying specific applications that align with market demands will be essential for driving interest in antimatter energy. Monitoring developments in related fields, such as fusion energy and advanced battery technologies, will also be important. These innovations could influence the trajectory of antimatter energy demand and its competitive positioning in the market. Keeping abreast of emerging technologies will help inform strategies for advancing antimatter research and applications. The future of antimatter energy will depend on a combination of technological advancements, market dynamics, and public interest. As researchers continue to explore the possibilities, the demand for antimatter as an energy source could grow significantly. The journey into the world of antimatter energy is just beginning, filled with potential for transformative change. Government and private funding play critical roles in advancing antimatter research and technology. As the potential applications of antimatter energy become more apparent, securing financial support is essential for pushing the boundaries of what can be achieved. Both sectors must collaborate to foster innovation and drive progress in this fascinating field. Public funding often provides the foundation for initial research initiatives in antimatter science. Government grants and support can help institutions acquire the necessary resources to conduct experiments and develop technologies. These investments are vital for laying the groundwork that will attract further interest and investment from private entities. Private funding sources, including venture capital and corporate investment, are increasingly recognizing the potential of antimatter. Companies involved in aerospace, energy, and medical technologies are exploring how antimatter can enhance their products and services. This interest can lead to significant financial commitments that drive research and development efforts. The synergy between government and private funding can create a robust ecosystem for antimatter research. By aligning their goals and resources, both sectors can maximize their impact. Collaborative projects can leverage the strengths of each, ensuring that scientific advancements translate into practical applications. Research institutions and universities often seek partnerships with industry to secure funding for antimatter projects. These collaborations can provide access to additional financial resources and expertise. Engaging with private companies allows researchers to align their work with real-world applications, increasing the relevance and potential for funding. Furthermore, successful pilot projects funded by government or private investors can serve as proof of concept. Demonstrating the feasibility of antimatter applications can attract additional funding and interest from other stakeholders. A track record of success can build confidence in the viability of antimatter technologies, encouraging more investments. Public-private partnerships are also instrumental in addressing the economic challenges associated with antimatter. Combining resources allows for a more comprehensive approach to overcoming the hurdles of production and cost. These partnerships can facilitate the development of new technologies that lower the barriers to entry for antimatter applications. Grants specifically targeted at clean energy initiatives may provide additional opportunities for antimatter research funding. As governments prioritize sustainable energy solutions, antimatter could align with these objectives. Pursuing funding through clean energy programs can enhance the visibility and support for antimatter projects. Additionally, educational outreach about the potential of antimatter is crucial for attracting funding. Engaging the public and policymakers can raise awareness of the benefits and applications of antimatter. Increased understanding can lead to more robust support from government entities and private investors alike. Investors are likely to be more inclined to support antimatter projects if there is a clear pathway to commercialization. Identifying specific market needs and demonstrating how antimatter can meet those needs will be essential. Articulating the potential return on investment can significantly influence funding decisions. The role of advocacy groups and organizations promoting scientific research cannot be underestimated. These entities can lobby for increased government funding and support for antimatter initiatives. Their efforts can help ensure that antimatter research receives the attention and resources it needs to thrive. Ultimately, the future of antimatter research will depend on the collaborative efforts of government, industry, and research institutions. By working together to secure funding and resources, stakeholders can drive innovation in antimatter technology. This partnership will be essential for unlocking the immense potential that antimatter holds for energy and exploration. The explosion risk associated with antimatter release is one of the most significant safety concerns in the field. When antimatter encounters matter, they annihilate each other, resulting in a tremendous release of energy. This annihilation produces gamma rays and other particles, creating potentially catastrophic consequences if not properly contained. Even a minuscule amount of antimatter can yield an explosion equivalent to a significant amount of conventional explosives. For instance, just a gram of antimatter could produce energy comparable to 20 kilotons of TNT. The implications of such energy release highlight the critical need for stringent safety protocols in antimatter research and applications. Containment systems for antimatter must be meticulously designed to prevent any interaction with matter. Current methods involve using magnetic fields or vacuum environments to isolate antimatter particles. However, even the slightest fluctuation in these containment systems can result in dangerous breaches. Monitoring the stability of antimatter containment is crucial for mitigating explosion risks. Continuous observation systems must be in place to detect any deviations from optimal conditions. By implementing real-time monitoring, researchers can respond swiftly to potential threats before they escalate into catastrophic incidents. Emergency response plans are essential components of any research facility working with antimatter. These plans should outline procedures for containment breaches, including evacuation protocols and communication strategies. Ensuring that all personnel are trained in these procedures can help minimize risks in the event of an emergency. The complexity of antimatter storage and handling requires a specialized workforce trained in safety protocols. Individuals working with antimatter must understand the unique risks and be equipped to handle emergencies effectively. Investing in training programs can enhance safety and ensure that researchers are prepared for any eventuality. Public perception of the risks associated with antimatter can influence funding and support for research initiatives. Engaging in transparent discussions about the safety measures in place can help alleviate fears surrounding antimatter. Building public trust is essential for fostering an environment where antimatter research can thrive. Regulatory frameworks governing the use of antimatter must be robust and comprehensive. These regulations should address safety protocols, containment standards, and emergency response procedures. By establishing clear guidelines, governments can promote responsible research practices while minimizing risks. The exploration of antimatter's potential in various applications requires a commitment to safety. Researchers must prioritize risk assessment and mitigation strategies in every stage of antimatter development. Ensuring that safety remains a top priority will be crucial for advancing antimatter technologies responsibly. Ongoing research into advanced containment materials and methods may enhance safety measures further. Innovations in materials science can lead to more effective ways of isolating antimatter, reducing the chances of accidental release. As technology progresses, the potential for safer antimatter storage systems becomes increasingly feasible. Collaboration between scientists, engineers, and safety experts is vital for addressing the explosion risks of antimatter. By pooling knowledge and resources, the scientific community can develop best practices for handling antimatter safely. This collaborative effort can drive advancements that ensure the responsible use of antimatter in various applications. As research into antimatter continues, understanding and mitigating the risks associated with its release will remain paramount. Each step forward in safety technology can contribute to making antimatter a more viable energy source. The journey toward harnessing antimatter's potential will depend on maintaining rigorous safety standards throughout the process. The potential threats to human life and infrastructure posed by antimatter are significant and must be carefully considered. If antimatter were to be released in an uncontrolled manner, the consequences could be catastrophic. The energy produced from a small amount of antimatter could cause extensive damage to surrounding areas, jeopardizing both lives and property. Accidental interactions between antimatter and matter are the primary concern in terms of safety. In a laboratory setting, any breach in containment could lead to immediate annihilation and a release of energy. This underscores the need for rigorous safety protocols to minimize the risk of such incidents occurring. Infrastructure designed to support antimatter research must also adhere to strict safety standards. Facilities need to be constructed with materials capable of withstanding the potential energy release associated with antimatter. This careful design is essential to protect not just the research staff, but also the surrounding community. The psychological impact on the public regarding antimatter's potential threats can also pose challenges. Fear of the unknown can lead to resistance against research initiatives and funding. Educating the public about the safety measures in place and the benefits of antimatter technology is vital for gaining support. In the event of an antimatter-related incident, emergency response plans must be thoroughly developed and tested. These plans should include evacuation routes, communication strategies, and medical response protocols. Training first responders to handle such unique situations is crucial for mitigating the impact of an incident. Additionally, the strategic location of antimatter research facilities plays a role in minimizing risks. Placing these facilities in areas less populated can help reduce potential casualties in the event of an accident. Evaluating the geographical and demographic factors is essential for ensuring safety. The potential for malicious use of antimatter also raises significant concerns. As research advances, the possibility of antimatter being weaponized cannot be ignored. This threat necessitates international regulations and agreements to prevent the misuse of antimatter technology. Safety measures should also extend to transportation of antimatter. Any movement of antimatter must be handled with the utmost care to prevent accidents. Developing secure transport protocols will be critical for ensuring that antimatter can be moved safely between facilities. Furthermore, public infrastructure, such as power grids and transportation systems, could be affected by the consequences of an antimatter incident. The energy released could disrupt essential services and lead to widespread chaos. Planning for these contingencies is essential for maintaining societal stability. Research into antimatter must continuously assess and address potential threats to human life. As technology evolves, so too should the strategies for managing associated risks. A proactive approach to safety will ensure that advancements in antimatter research do not come at the cost of public safety. International collaboration in safety standards and threat assessments can enhance the global response to potential antimatter risks. By sharing best practices and knowledge, countries can collectively work to mitigate threats. This cooperation is vital in establishing a framework for responsible research and use of antimatter technology. The focus on safety and risk management will ultimately shape the future of antimatter research. Ensuring that human life and infrastructure are protected must remain a top priority. As we explore the possibilities of antimatter, we must also remain vigilant in addressing the challenges it presents. The risks of antimatter misuse present serious concerns that cannot be overlooked. As with any powerful technology, the potential for malicious applications exists, raising alarm bells among scientists and policymakers alike. The ability to harness such immense energy can attract not only legitimate research, but also those with harmful intentions. One primary concern is the possibility of antimatter being weaponized. If antimatter were to fall into the wrong hands, it could be used to create devastating explosive devices. The energy released from even a small amount of antimatter could result in catastrophic destruction, making it a potent tool for terrorism or warfare. The dual-use nature of antimatter technology complicates regulatory frameworks. While antimatter holds great promise for energy generation and scientific advancements, its potential for misuse requires stringent oversight. Establishing clear guidelines and regulations is essential to prevent the exploitation of antimatter research for harmful purposes. Additionally, the production facilities for antimatter are at risk of being targeted. The infrastructure required to generate antimatter is complex and expensive, making it a valuable target for those with malicious intent. Ensuring that these facilities are adequately protected is crucial for safeguarding against potential attacks. Public fear surrounding the misuse of antimatter can hinder research initiatives. Concerns about safety and security may lead to resistance against funding and support for antimatter projects. Addressing these fears through transparency and education will be vital for fostering a supportive environment for research. International cooperation is necessary to combat the risks associated with antimatter misuse. Countries must work together to establish treaties and agreements that address the handling and distribution of antimatter technology. This collaborative effort can help create a unified approach to regulating the research and application of antimatter. Moreover, robust monitoring systems are needed to track antimatter production and usage. Implementing stringent controls can deter illicit activities and ensure that antimatter is used solely for beneficial purposes. These monitoring systems will be crucial for maintaining oversight in a rapidly evolving field. Training personnel in the safe handling of antimatter also plays a role in minimizing misuse risks. Individuals working in antimatter research must be educated about the ethical implications and potential dangers associated with their work. Fostering a culture of responsibility among researchers is essential for ensuring that antimatter technology is developed safely. The potential for theft of antimatter poses another significant threat. Even small quantities of antimatter, if stolen, could lead to catastrophic consequences. Developing advanced security measures to protect antimatter storage and production facilities is essential for preventing such incidents. Public engagement is crucial in addressing the societal concerns surrounding antimatter misuse. Promoting informed discussions about the benefits and risks can enhance understanding and alleviate fears. Increased awareness may lead to stronger support for research initiatives that prioritize safety and ethical considerations. Ongoing risk assessments should be a fundamental part of antimatter research. As technology evolves, new threats may emerge that necessitate updated safety protocols and regulations. A proactive approach to identifying and addressing potential misuse will be critical for advancing antimatter technologies responsibly. Ultimately, the exploration of antimatter's potential must go hand in hand with an awareness of its risks. While the possibilities for beneficial applications are vast, vigilance against misuse is essential. By prioritizing safety and ethics, the scientific community can work toward harnessing antimatter responsibly for the betterment of society. Mitigating the risks associated with antimatter requires a multifaceted approach that encompasses safety protocols, technological advancements, and regulatory measures. One fundamental solution involves establishing rigorous safety standards for production and storage facilities. Implementing these standards can significantly reduce the likelihood of accidental releases and ensure the secure handling of antimatter. Investing in advanced containment technologies is another crucial step in risk mitigation. Utilizing cutting-edge materials and innovative designs can enhance the effectiveness of storage systems. Improved containment methods will help minimize the risk of antimatter interacting with regular matter, thus preventing catastrophic outcomes. Continuous monitoring of antimatter facilities is essential for maintaining safety. Real-time data collection can provide insights into the stability of containment systems, allowing for immediate corrective actions if necessary. This proactive approach ensures that any potential issues are addressed before they escalate into serious threats. Training personnel in the safe handling of antimatter plays a pivotal role in mitigating risks. Comprehensive education programs should emphasize not only technical skills, but also the ethical implications of working with such powerful technology. A well-trained workforce is better equipped to manage safety protocols and respond to emergencies effectively. Developing robust emergency response plans is critical for any facility engaged in antimatter research. These plans should outline clear procedures for dealing with containment breaches, including evacuation routes and communication strategies. Regular drills and training sessions will prepare staff to act swiftly and efficiently in the event of an incident. International collaboration can significantly enhance efforts to mitigate antimatter-related risks. By sharing knowledge, resources, and best practices, countries can work together to develop comprehensive safety frameworks. This global cooperation will foster a unified approach to managing the challenges associated with antimatter research. Establishing regulatory bodies to oversee antimatter research and applications can help ensure that safety measures are consistently implemented. These organizations can create guidelines for the production, storage, and transportation of antimatter, providing a structured framework for responsible use. Clear regulations will enhance public trust and promote accountability in the field. Public engagement is also crucial in addressing concerns surrounding antimatter risks. Open dialogues about the benefits and challenges of antimatter can help alleviate fears and build support for research initiatives. Educating the public about the safety measures in place will foster a greater understanding of the technology, Creating a culture of responsibility within research institutions is vital for risk mitigation. Encouraging scientists and engineers to prioritize safety in their work will lead to more conscientious practices. This cultural shift can enhance overall awareness of the potential dangers associated with antimatter. Investing in research aimed at improving production methods is another effective solution. As technology evolves, finding ways to produce antimatter more efficiently can reduce the energy costs and risks associated with its generation. Innovations in this area could make antimatter more accessible, while ensuring safe handling procedures are in place. Implementing advanced security measures at antimatter research facilities will help prevent theft and unauthorized access. Surveillance systems, access controls, and regular security audits can deter potential threats. By ensuring that only authorized personnel have access to antimatter, facilities can protect against malicious misuse. Finally, ongoing risk assessments are essential for adapting to the evolving landscape of antimatter research. As new technologies and methodologies emerge, it is crucial to evaluate their implications for safety and security. Continuous vigilance will ensure that the scientific community remains prepared to address emerging challenges associated with antimatter. Establishing international regulations for antimatter handling is essential to ensure safety and prevent misuse. As antimatter technology advances, a unified framework can help manage the unique risks associated with this powerful energy source. Coordinated efforts among nations will be crucial for developing comprehensive guidelines that govern the production, storage, and transportation of antimatter. One primary focus of these regulations should be safety standards for facilities engaged in antimatter research. These standards must outline the necessary containment measures and operational protocols to mitigate risks effectively. By adhering to these guidelines, facilities can enhance their safety measures and reduce the potential for accidents. Training and certification requirements for personnel working with antimatter should also be included in the regulatory framework. Ensuring that individuals are adequately trained in handling antimatter safely is critical for preventing incidents. A standardized training program will help promote a culture of safety across international research institutions. Furthermore, international regulations should address the transportation of antimatter. Given the risks associated with accidental release, strict guidelines for the movement of antimatter must be established. These regulations can help ensure that antimatter is transported securely and responsibly, minimizing the potential for mishaps. Emergency response protocols should be an integral part of international regulations for antimatter. Clear guidelines outlining the steps to take in the event of an incident will be vital for safeguarding human life and infrastructure. Establishing these protocols can ensure that researchers and first responders are prepared to act swiftly and effectively. The potential for antimatter to be weaponized raises significant concerns that must be addressed in regulatory discussions. International agreements should include provisions aimed at preventing the misuse of antimatter for malicious purposes. Establishing a clear legal framework can deter individuals or groups from attempting to exploit antimatter technology. Public engagement in the development of international regulations is also essential. Educating the public about the importance of safe antimatter handling and the measures in place can foster trust and support for research initiatives. Transparency in regulatory discussions can help alleviate fears surrounding the risks associated with antimatter. Collaboration between governments, scientific communities, and industry stakeholders will be crucial for creating effective regulations. By pooling resources and expertise, these groups can develop comprehensive guidelines that consider the diverse aspects of antimatter research. This collaborative effort will enhance the overall effectiveness of regulatory frameworks. The regulations should also account for ongoing research and advancements in antimatter technology. As the field evolves, regulations must adapt to address new challenges and opportunities that arise. Regular reviews and updates to international guidelines will ensure that they remain relevant and effective. International organizations can play a pivotal role in facilitating discussions and negotiations surrounding antimatter regulations. By providing a platform for dialogue, these organizations can help establish consensus among nations on best practices for antimatter handling. Their involvement can lead to the creation of standardized protocols that enhance global safety. In addition, establishing a reporting system for incidents involving antimatter will contribute to regulatory transparency. Countries should share information about any accidents or near misses to learn from each other's experiences. This open exchange of information can help improve safety practices and prevent similar incidents in the future. Lastly, the development of international regulations for antimatter handling can serve as a model for other emerging technologies. By addressing the unique challenges posed by antimatter, policymakers can create frameworks that may be applicable to other high-risk fields. This proactive approach will help ensure that advancements in science and technology prioritize safety and responsibility. Achieving the full potential of antimatter as an energy source requires significant technological breakthroughs. Current production methods are not efficient enough to make antimatter practical for widespread use. Innovations are needed to enhance the efficiency of particle accelerators and other production techniques. Improved containment systems are essential for safely managing antimatter. The development of advanced materials that can withstand the unique challenges of antimatter storage will be crucial. These innovations could reduce the risks associated with accidental release and enhance safety protocols. Researchers must also explore alternative production methods that can generate antimatter more cost-effectively. Techniques such as laser-based production or harnessing cosmic rays could provide new avenues for antimatter generation. Finding viable alternatives could drastically lower production costs and improve accessibility. Automation and artificial intelligence may play a role in optimizing antimatter production processes. Implementing smart technologies can enhance precision and reduce human error in handling antimatter. These advancements will contribute to safer and more efficient production environments. The energy extraction methods from antimatter also require breakthroughs. Developing effective ways to harness the energy released during antimatter annihilation is crucial for practical applications. Innovative designs for antimatter reactors or engines will be needed to convert that energy into usable power. Advancements in monitoring technologies will enhance the safety and efficiency of antimatter research. Real-time data analysis can provide insights into containment stability and production processes. Improved monitoring systems can help researchers respond quickly to any anomalies or risks. Collaboration between disciplines such as materials science, physics, and engineering will be vital for driving these breakthroughs. Interdisciplinary research can lead to innovative solutions that address the multifaceted challenges of antimatter technology. This collaborative spirit can foster a culture of creativity and problem-solving. Regulatory frameworks must evolve alongside technological advancements in antimatter. Developing clear guidelines for the safe use of new technologies will be essential for public trust. Policymakers need to work closely with scientists to ensure that regulations reflect the realities of antimatter research. Investment in research and development will be a key driver of technological breakthroughs. Securing funding for antimatter initiatives can accelerate the pace of innovation and discovery. A commitment to long-term research will enable scientists to explore the full spectrum of antimatter applications. Public-private partnerships can play a significant role in advancing antimatter technology. Collaborations between governments, academic institutions, and private companies can pool resources and expertise. This cooperative approach can lead to significant advancements in antimatter research and its practical applications. Education and training programs focused on antimatter technology are essential for fostering a skilled workforce. Preparing the next generation of scientists and engineers will ensure that the field continues to evolve. A well-informed workforce will be better equipped to drive innovations in antimatter production and application. Lastly, continuous assessment of the societal implications of antimatter breakthroughs is necessary. As new technologies emerge, their potential impact on communities and the environment must be evaluated. By prioritizing responsible development, the scientific community can work toward harnessing antimatter for the greater good. Predictions for the next 50 years regarding antimatter research and its applications are both exciting and ambitious. As advancements in technology continue, we can expect significant progress in antimatter production efficiency. Researchers will likely develop new methods that drastically reduce costs and increase output, making antimatter more accessible. The integration of antimatter energy into mainstream energy systems could become a reality within the next few decades. This could revolutionize power generation, offering a clean and virtually limitless energy source. As nations shift towards sustainable practices, antimatter may play a pivotal role in global energy strategies. Antimatter propulsion systems for space exploration could also see substantial developments. As our aspirations for interplanetary travel grow, antimatter could provide the necessary thrust for spacecraft. This technology could enable missions to Mars and beyond, significantly reducing travel times compared to conventional methods. Collaboration among nations will likely enhance advancements in antimatter technology. As global challenges such as climate change require collective action, countries may work together to share knowledge and resources. This international cooperation could foster innovation and lead to breakthroughs that benefit all. Public perception of antimatter will evolve as research progresses and safety measures are established. Increased transparency about the potential benefits and risks will help build trust among communities. As awareness grows, public support for antimatter initiatives may strengthen, leading to greater investment and research opportunities. The ethical implications of antimatter research will be more widely discussed in the coming years. As the technology matures, societies will grapple with questions regarding its responsible use and potential for weaponization. Engaging in these conversations will be essential for ensuring that antimatter serves the greater good. Educational initiatives will play a crucial role in shaping the future of antimatter research. Training programs focused on antimatter science will equip the next generation of scientists and engineers with the skills needed to innovate. A well-prepared workforce will be vital for driving advancements in the field. Innovative containment and safety technologies are expected to evolve alongside antimatter research. As researchers gain more insights into the behavior of antimatter, improved methods for safe storage and handling will emerge. These advancements will enhance safety protocols and reduce risks associated with antimatter. The potential applications of antimatter in medicine may also see significant growth. As research progresses, new medical technologies that utilize antimatter principles could emerge. This could lead to advancements in diagnostic imaging and targeted treatments, improving healthcare outcomes. Economic models surrounding antimatter energy will likely develop as its viability increases. As production costs decrease, the market for antimatter energy could expand, attracting investments from various sectors. This economic shift may lead to the establishment of new industries focused on antimatter technologies. Regulatory frameworks will need to adapt to the evolving landscape of antimatter research. Governments and international bodies will have to establish guidelines that prioritize safety and ethical considerations. Developing comprehensive regulations will be essential for managing the risks associated with antimatter. Finally, the integration of antimatter into existing energy systems will be a gradual process that requires careful planning. Researchers will need to demonstrate the practicality and safety of antimatter applications to gain public and governmental support. This journey will unfold over the next 50 years, shaping the future of energy and exploration. Antimatter's place in the global energy mix could evolve dramatically over the coming decades as technology advances. With its potential for high energy output and zero emissions, antimatter presents a unique opportunity to complement existing energy sources. Integrating antimatter energy could enhance the diversity and resilience of the global energy portfolio. As nations increasingly seek sustainable alternatives to fossil fuels, antimatter may emerge as a critical player in the transition to clean energy. Its ability to provide concentrated energy with minimal environmental impact aligns with global efforts to reduce carbon emissions. This alignment with sustainability goals could facilitate broader acceptance of antimatter technologies. Incorporating antimatter into the energy mix will require substantial investments in research and infrastructure. Governments and private sectors will need to collaborate to develop the necessary facilities for production and storage. Building these infrastructures will be essential for realizing the full potential of antimatter as an energy source. The potential for antimatter to enhance energy security is another significant factor. As countries diversify their energy supplies, antimatter could reduce reliance on traditional energy sources and geopolitical tensions associated with fossil fuel dependency. By harnessing antimatter, nations may achieve greater energy independence. Antimatter could also serve as a bridge technology during the transition to renewable energy sources. As societies move towards solar, wind, and other renewables, antimatter may provide reliable backup power, This capability can help stabilize energy grids and ensure a consistent energy supply. Public perception will play a crucial role in determining antimatter's place in the energy mix. As awareness of its potential benefits and safety measures grows, public support for antimatter initiatives may increase. Educating communities about the advantages of antimatter energy will be essential for fostering acceptance. International collaboration on antimatter research can enhance its integration into the global energy framework. By sharing knowledge and resources, countries can work together to overcome challenges associated with antimatter development. This collaborative spirit can lead to innovative solutions and accelerate the adoption of antimatter technologies. The economic implications of incorporating antimatter into the energy mix must also be considered. As production methods become more efficient, the costs associated with antimatter could decrease. A favorable economic environment will be essential for attracting investments and making antimatter a viable option for widespread energy use. In terms of energy density, antimatter surpasses all current fuel sources. This unparalleled efficiency makes it a compelling alternative for high-demand applications, such as space travel and large-scale power generation. As technology advances, the energy density of antimatter could revolutionize how we approach energy consumption. The potential for antimatter to impact various sectors beyond energy is also noteworthy. Applications in medicine, transportation, and aerospace could benefit from advancements in antimatter technology. Integrating antimatter into these fields can lead to cross-disciplinary innovations that further enhance its role in society. Regulatory frameworks will need to adapt to accommodate the unique aspects of antimatter energy. Developing comprehensive regulations that prioritize safety and ethical considerations will be crucial for public confidence. Clear guidelines can facilitate the responsible development of antimatter as a legitimate energy source. As the global energy landscape continues to evolve, antimatter's place in the mix will depend on a collective commitment to innovation and collaboration. Balancing the risks and rewards associated with antimatter will be key to harnessing its potential for the benefit of all. The journey to integrate antimatter into the energy mix promises to be a transformative endeavor in the years to come. The question of whether antimatter will replace other energy sources is complex and multifaceted. While antimatter offers exceptional energy density and minimal environmental impact, it currently faces significant production and cost challenges. The transition to antimatter as a mainstream energy source will require substantial advancements in technology and infrastructure. Current energy systems are deeply entrenched, relying on a mix of fossil fuels, nuclear power, and renewables. Antimatter would need to demonstrate clear advantages over these established sources to gain widespread acceptance. This includes proving not only its efficiency, but also its safety and reliability in various applications. As research progresses, antimatter may serve as a complement rather than a direct replacement for existing energy sources. For instance, it could provide backup power in renewable energy systems, addressing intermittency issues associated with solar and wind. This synergy could enhance the overall stability of energy grids while maintaining a diverse energy mix. The potential for antimatter in specific applications, such as space exploration, is particularly promising. As humanity aims for deeper space missions, conventional propulsion systems may not suffice. Antimatter propulsion could enable faster travel, making it a critical technology for interplanetary exploration. Economic considerations will significantly influence antimatter's role in the energy landscape. If production costs can be reduced through technological breakthroughs, antimatter may become more viable for various applications. The economic viability of antimatter will determine how it fits into the broader energy ecosystem. Public perception and acceptance of antimatter technology will also play a vital role in its adoption. Misinformation and fear surrounding the risks of antimatter could hinder its integration into energy markets. Education and transparency will be essential to building trust and promoting informed discussions about antimatter's potential. The regulatory environment will need to adapt to accommodate the unique aspects of antimatter. Establishing clear guidelines for its production, storage, and use is crucial for ensuring safety and public confidence. A supportive regulatory framework can facilitate the responsible development of antimatter technologies. International collaboration on antimatter research can accelerate progress and innovation. By pooling resources and expertise, nations can address challenges collectively, making antimatter technologies more accessible. This cooperation can foster a global commitment to exploring the benefits of antimatter as an energy source. Antimatter may also drive advancements in related fields, such as materials science and energy efficiency. Innovations developed for antimatter applications could lead to breakthroughs that benefit other energy sources. This interconnectedness can enhance the overall progress in energy research and development. The environmental implications of antimatter must be carefully considered in the context of replacing other energy sources. While antimatter itself produces no emissions, the processes used to produce and store it could have ecological consequences. A thorough assessment of the environmental impact will be necessary for responsible energy planning. Ultimately, whether antimatter will replace other energy sources remains uncertain. Its integration into the global energy mix will depend on a combination of technological advancements, public acceptance, and regulatory support. As researchers continue to explore antimatter's potential, its future in the energy landscape will unfold in intriguing ways. Harnessing antimatter has the potential to create profound societal impacts that extend beyond energy production. If successfully developed, antimatter could provide a clean and virtually limitless energy source, addressing global energy shortages. This shift could enhance the quality of life for communities around the world by providing access to reliable power. The advent of antimatter technology may significantly influence economic structures and job markets. New industries could emerge focused on antimatter production, research, and applications. This growth would create numerous job opportunities, requiring a skilled workforce trained in advanced technologies and safety protocols. Moreover, the integration of antimatter into energy systems could contribute to environmental sustainability. By reducing reliance on fossil fuels, societies could lower their carbon emissions and mitigate climate change effects. The widespread adoption of antimatter could lead to cleaner air and healthier ecosystems. Educational institutions will need to adapt to the changing landscape brought about by antimatter research. Curricula may evolve to include specialized training in antimatter technologies and related fields. Preparing the next generation of scientists and engineers will be crucial for sustaining advancements in this area. Public perception of antimatter technology will play a vital role in its acceptance and integration. Misinformation and fear surrounding antimatter must be addressed through effective communication and education. Building public trust will be essential for ensuring support for antimatter initiatives. Ethical considerations will also arise as societies grapple with the implications of antimatter use. Discussions about the moral responsibilities associated with harnessing such powerful technology will be necessary. Engaging diverse stakeholders in these conversations can lead to a more comprehensive understanding of the ethical landscape. International collaboration in antimatter research can promote global unity and shared goals. As countries work together to explore antimatter's potential, they can foster diplomatic relationships. This cooperation can strengthen alliances and encourage peaceful scientific endeavors. The potential for antimatter to influence healthcare is another significant societal impact. Applications in medical imaging and treatment could revolutionize diagnostics and therapies. By enhancing healthcare technologies, antimatter could lead to better health outcomes and increased life expectancy. Furthermore, the advancements driven by antimatter research may have cascading effects on various sectors. Breakthroughs in materials science and engineering could enhance other technologies, leading to innovations across industries. This interconnectedness can spur economic growth and improve the quality of life. As societies adapt to the changes brought about by antimatter, policy frameworks will need to evolve. Governments must establish regulations that prioritize safety and ethical considerations in antimatter development. Creating comprehensive policies will help manage risks while promoting responsible research. Antimatter technology could also reshape the geopolitical landscape. Nations that successfully harness antimatter may gain significant strategic advantages in energy and defense. This shift could lead to a re-evaluation of power dynamics on the global stage. Ultimately, the societal impacts of harnessing antimatter are vast and complex. The technology has the potential to drive significant advancements across multiple sectors while presenting new challenges. As research progresses, understanding and addressing these impacts will be crucial for navigating the future of antimatter technology. In this video, we explored the fascinating world of antimatter and its potential implications for our future. From understanding the basic composition of antimatter to discussing its unique properties, we have seen how this extraordinary substance could revolutionize energy production and various industries. Antimatter's energy density far surpasses that of traditional fuels, highlighting its promise as a clean and virtually limitless power source. We delved into the differences between antimatter and regular matter, emphasizing the concept of annihilation and its energy release. The potential for harnessing this energy opens doors to innovative applications, including propulsion systems for space travel and breakthroughs in medical technology. However, we also examined the significant challenges associated with antimatter, particularly in terms of production costs and containment methods. Safety and ethical considerations surrounding antimatter were also central to our discussion. We highlighted the risks of misuse and the need for stringent international regulations to ensure responsible development. The importance of global cooperation in addressing these challenges cannot be overstated, as nations work together to unlock the potential of antimatter while prioritizing safety. The future of antimatter technology appears promising, with predictions suggesting it could play a vital role in the global energy mix. As research continues to advance, we can anticipate a more significant integration of antimatter into our energy systems, contributing to environmental sustainability and energy security. This could have lasting impacts on economies, job markets, and public health. Furthermore, we addressed the societal implications of harnessing antimatter, emphasizing the need for education and public awareness. As antimatter technologies evolve, preparing the next generation of scientists and engineers will be essential for driving innovation in this field. Ethical discussions surrounding antimatter's applications will also shape how society approaches its development. Throughout our exploration, we acknowledge the balance between competition and collaboration among nations in the realm of antimatter research. Striking this balance will be crucial for maximizing the benefits while minimizing risks associated with this powerful technology. The role of international organizations in promoting safety and cooperation cannot be overlooked. As we concluded our deep dive into antimatter, we hope you found the information both enlightening and thought-provoking. The journey to harness antimatter is just beginning, and the possibilities it presents for our future are vast. It's an exciting time to be involved in the pursuit of advanced energy solutions. If you enjoyed this video and want to keep up with the latest developments in antimatter and other cutting-edge topics, please like and subscribe to our channel. Your support helps us create more engaging content for you. Don't forget to check out the rest of the videos on our channel, where we cover a wide range of scientific advancements and their implications for society. Thank you for watching, and we look forward to seeing you in the next video.